Hello.
Okay, so welcome to the final day of the ISM 25. Today's morning session, we have 3 talks, first by Lognagam, then Pramod, and one by Suchentan Das. So we'll start with Loga's talk, which is on solvable models of heat transport in quantum mechanics.
Okay. Good morning, everyone, and I should congratulate the organizers for pulling off this conference despite all this unforeseen drama with Indigo and so on. And I should also thank all of you for being present at the last day of this conference. Okay, on a Sunday, nevertheless. So today I wanted to tell you guys about some work I did with Prithvi, who's in the audience, and his ex-student Swati, both of them from IIT Palakkad. Okay, and so and the main subject of this talk, okay, presenting this in a string conference, is actually the underlying subject is double scaled SYK models and the kind of thing that we can do with it. But there's a particular physical problem that we are interested in, which I'll describe in a moment, and which we studied using double scale SYK and its solution. So there's some kind of a preamble, okay, to motivate the problem. And we also understood that after understanding double scale SYK in its full glory, that perhaps to understand what it is doing, it's good to kind of first think about somewhat simplified, maybe even oversimplified models of this problem. So that's what I'll start with. So that's like a broad big this thing. So this is the basic question. So the basic question we are asking is somewhat like this. So we are interested in two quantum mechanical systems. So I'll call one system as a hot system at a higher temperature and a cold system at a lower temperature. Okay. So there are thermal equilibrium for t less than 0. They are not talking to each other for t less than 0. At t equal to 0, I connect them. Okay. I connect them using some operator. Okay, one operator in the hot system and another operator in the cold system. I multiply and then I turn on the interaction Hamiltonian, okay, of that form at t equal to 0. Okay, and for some, to simplify this analysis, I'll just assume that these operators themselves initially had 0 thermal expectation values. Okay, and the basic question is what happens? What happens after you connect them? Okay, so this is the question. So there's a kind of an intuitive answer to this question, okay, which is that well, when you connect them, okay, there's some transient, okay, at equal to 0, but eventually, what happens is that there's a heat current which starts flowing from the hot system to the cold system. Okay, there's some steady state current. So there's a transient regime and then there's a steady state regime, and if you wait for sufficiently long, eventually both of them will come to same temperature and they will equilibrate. Okay, so then there's equilibration regime. Okay, but if there are two very big systems, then equilibration regime might take some time. Okay, and so these are the three regimes. Okay, I'm not, and at least this is true if your system is not integrable, or it doesn't have like a lot of conserved quantities or something. Any realistic system, basically you expect it to do these things. Okay, so what we will be interested in this talk is to try to understand what happens in these first two regimes. I'll not talk about the equilibration regime. So I'm interested in what happens at the transient level, okay, which is actually a very hard question. Okay, and then there's a question of what happens with the steady state, like when we have steady state peak current, which is the kind of questions one often asks and answers. It's a slightly easier question to answer, okay, because it's a kind of a steady state problem. Okay, it's still a non-equilibrium problem, but at least you can kind of use some steady state Kubo formalism or something like that to answer that. Okay, the transients are hard, okay, and they're very hard to solve in any realistic systems. Okay, But I want to kind of emphasize in this talk that you can kind of make a lot of progress by thinking about it by making some toy models. Okay, so these are the questions. Now this has some like relations to holography and so on and so forth, as pointed out. This problem as pointed out by this Almheri, Milenkin and Swingle in a 2019 paper. I won't talk about the holography, but aspect of it I will mainly talk about just the quantum mechanics system aspect of it. Okay, but just to say there is it has some connection to average null energy condition and things like that, which I won't talk about. Okay, but they are kind of there in the background, and if you want, like you can go back and look at what they say and how it compares with what we say and so on. Okay, so so what are the questions? The question is that like so there's some transient. The question is what kind of transients do you expect? Okay, so transients you expect is that what you expect is some kind of like a heat spark or heat surge, as they call it. Okay, which is basically like when you connect it, okay, immediately you get like some both of them, both the hot system and cold system, kind of like get heated up slightly. Okay, and then they eventually it settles down to like the steady current which flows from this thing. So this heating up is kind of symmetric in the sense that like both the hot system and the cold system gets heated up. Okay, because it just like some shock or some surge which doesn't like so much care about like which is hot and which is cold, but it's more like like the thing that just comes about by just connecting the fact that you're doing it at t equal to 0, okay, sharply, and then like it will go to steady state. But then we want to understand how does it go to steady state? Does it grow? Does it like exponentially fast? Does it go like some e to the power minus t? Okay, or does it go like some power law? Okay, and then like when it reaches a steady state, there is some kind of a Fourier's law kind of thing where you expect that the heat current is proportional to the temperature difference. This proportionality constant is the thermal conductance. Okay, and then you want to ask, so how does this thermal conductance scale with this temperature? Let's say both of them are about the same temperature, slightly different. Okay, then this average temperature, how does it depend on those things? Those are the kind of questions, natural physical questions that we're interested in. So let's kind of like set it up a bit and kind of set up some toy model and so on. So let's say I look at, for definiteness, like the energy of the cold system, okay, and how does it change. So I will call that EC dot, okay, the rate of the heat current, okay, from the cold system. How does the energy of the cold system change? Okay, there's some set of things you can do, some basic perturbation theory you can do. Okay, since the expectation values vanish of these operators, you go to second order in perturbation theory, and you basically get a formula like this. Okay, so a formula which basically relates like the EC dot in second order in perturbation theory between the coupling between the two systems, okay, in the interaction Hamiltonian, okay, to the Weitmann functions. So these G's are the Weitmann functions, which are basically defined like this, okay, for the coupling operators. Okay, so there's a remember, like my model was that there's a coupling operator in the hot system and there's a coupling operator in the cold system, and we are kind of combining them together. So GH is the Weitmann function of the hot coupling operator, and GC is the is that of the cold coupling operator, and and this dot, this overall dot means that you take a time derivative. Okay, and that's the thing. Okay, so now how does these Weitmann functions themselves look like? So you can kind of introduce some complete set of energy eigenstates, okay, within each of the systems, and you can kind of argue that this G of t basically has this kind of a spectral representation. Okay, so what is this? So this rho is basically density of states, okay, of energy eigenstates. Okay, so you basically have some energy eigenstates, and then this F is basically some matrix element square, okay, between the energy eigenstates, like averaged, like over energy eigenstates, okay, which is basically this average squared matrix element. So this is all somewhat straightforward. So this is the basic picture, okay, that G of t. So if I know this density of states, okay, and if I know this average matrix element square, okay, then I can feed this, I can calculate g of t, then if I know g of t, I can feed that there, okay, and then I can get, you know, like what the energy current should be, okay. So that's simple, okay. Are there any questions at this point? Or the operators are the ones by which the hot and cold system couple, okay. So the interaction Hamiltonian is made by some OH and OC operator, okay, okay. So the operators are the ones by which the two systems talk to each other.
This like systems.
I mean, what do you mean by role? This Hilbert space, there's an operator.
So like, do they create some states in this particular?
It could be anything. At this point, I'm being very general. Okay, it's some operator. Okay, some Hermitian operator. Okay, we will see particular operators. You know, like or rather, you know, like yeah, you know, some operator by which it couples. Okay, in the double scale SYK itself, I will tell you what kind of operators we are talking about. But in the time model, it's just some operator. Okay. I see the point is that, you know, like at some level we don't care what the operator is, provided we can model these things, okay, some density of states and so on, okay. Okay, so so this is the thing. So now, yeah, this is average over states of a given energy, okay. So there's some energy, there's some many states of a given energy, and you just kind of average over. So because this is states of a given energy, so I've kind of taken out the number of states of a given energy, but of course, you know, within degenerate energy levels, matrix elements can be different, but it doesn't matter because we are looking at some energy transport. So you just look at some aggregate and average, and then multiply by the total number of states. Okay. Okay. So the question in the F, yeah, and information about whether rho is about the system. Of course, F also contains information about the system. So okay, so given this thing, okay, so we have come so far. Now you might ask, okay, so let's make some simple models, okay, some simple-minded models, and let's see what happens and whether we can say something about it, okay. So of course, eventually we want to do this with double scale SYK, okay, with two double scale SYK and so on. But before that, let's kind of do some simple models, okay. So one of the simplest model, okay, is if you just take the density of states to be you know, like the density of states of a random matrix, okay. So which is basically a distribution like this, which is a Wigner semicircle, okay, as it is known, okay. And basically, you know, like so you have a semicircle of density of states, okay. So it has some edge, and you have a band of energies which is a continuum and so on, okay. Now and then, you know, like, so I need a model for F, okay. Now among these energy eigenstates, so I will again be very simple and not, you know, be, you know, like not come from any basic thing, but kind of make a phenomenological model where I will just take F to be something like this, okay. So this E naught is the energies. So the E naught are the edge energy. So this density of states goes from minus E naught to plus E naught. There's a semicircle, okay. And the point is that, you know, like so I may, you know, so if the delta is not there, basically what I'm saying is that I'm just taking it to be F naught, some constant, which basically means that I'm saying the operator basically couples all the energies to all the energies about equally, okay, by some strength F naught, which is a constant which does not depend on energy, okay. It's a very simple-minded model, okay. I can go slightly more, and I can add this delta term, okay. And what the delta term does is that it kind of in the semicircle, it kind of you know, like penalizes whether the two energies that you're connecting, okay, whether they are on the same side of the semicircle or not, okay. So the semicircle goes from negative energies to positive energies. If a negative energy and negative energy transitions go like 1 plus delta, and positive energy transition go like 1 plus delta, but positive and negative energies go like 1 minus delta, okay. So in some sense, you know, the delta suppresses across the energy transition. So it's, you know, it kind of, you can think of it as a cost if you kind of have to cross, you know, the middle of the semicircle, okay, to kind of, you know, like connect the energy states. So this is some model, okay, and it's simple polynomial, so that I can do my integrals and so on and so forth, okay. So then I can just start feeding that in, okay. So I have this model, I have some rho of E, some F of E, okay, and then I can just feed it into my equations, okay. So if I feed it, this is what I get. So I get a g of this form, okay, which is just some, it's all written in terms of Bessel function, some Bessel I functions, okay. You can just do these integrals, it's not, it's very simple, okay. Now you can calculate the g of t, okay. So this is all Bessel functions, and then you can ask, okay, so how does the g of t look like? It looks like some Bessel function by Bessel function, but you can ask, okay, how does it look like at large times, okay. So if you do that, what you see is something interesting, okay. So what you see is that, let's say you see something like 1 over t to the power 1 over t cube, okay, kind of fall off, okay. First of all, so there is a fall off of the Green's function, okay, the Weightman function, basically at large times, okay, as a power law, and the power is roughly goes like 1 over t cube, basically, okay. And over that you get some oscillations, okay. So it's kind of a power, you know, and then it wiggles a bit, okay, and the oscillations, okay, go like the sine 2 e naught and so on, okay, right, okay. Basically, you know, like this term goes like 1 plus delta. I mean, maybe I should have just multiplied 1 minus delta inside. This term goes like 1 plus delta. This term goes like 1 minus delta. So with 1 plus delta, you get some fall off, and 1 minus delta, you get a fall off and an oscillation. Okay, okay. So basically, if delta is 1, okay. So if delta is 1, basically you are kind of suppressing the across the energy, you know, transitions. Okay, then you know, like there is no oscillation. Okay, so the oscillation in some sense comes from, you know, like across the energy transitions, you can say, okay, and then there's a fall off. Okay, so this is the generic thing. Now I have a g of t. I can take two such random matrix models and then combine it, okay, and then ask what happens. Okay, so the heat current, I can't write down a simple formula, but it's a single integral, okay, which I can just do it, okay, just do it and plot it, you know, with very this thing, okay. And if I plot it, I get something like this, okay. So what does it look like? It's basically, this is the heat current, and as you connect it, it starts from 0, surges up, okay, reaches a maximum, then goes down, okay, maybe sometimes it wiggles a bit, but eventually goes to some constant state, okay, right, and then, you know, like and you can kind of convince yourself that this constant it goes to actually obeys Fourier's law, in the sense that, you know, like it is proportional to the temperature difference of these two random matrix dots, okay, right, you know, like, and if the temperature difference, you decrease it, it kind of saturates to lower, and if the temperature is equal, eventually it just saturates to 0, okay, right, okay. So that is this thing, very simple, okay, and that is the basic this thing, okay. So you can even now, given that we have a single integral, okay, I can even ask this question: how does it go towards this Fourier's law kind of steady state heat current, okay, at large times, which is again a question of is there a question? The surge doesn't care about temperature differences or anything, right, because surge is really about it's really the physics of connecting, okay, right. And then there's a surge, and in some sense the surge doesn't care about what the temperatures are at all, okay, that's the point. It doesn't care which is hot, which is cold, whether both of them are equally hot, doesn't care, because okay, that's the point, okay. At least in this model, that's what you see. And the good thing about this model is it's very simple. You know, you can, you know, any of you can just go back and, you know, just work it out, and you can just do this Bessel asymptotics, and you can just, you know, figure out, you know, like what the asymptotics is, and the asymptotics tells you that actually the approach, okay, I want you to first look at just the first term, first line, the approach to the infinite steady state, okay, the Fourier law steady state in this model is actually a power law, and the power is phi, okay, it goes like 1 over t to the power phi, okay. And you know, like and its coefficient is actually proportional. I mean, if you think of, you know, like the two temperatures being very close, they're proportional to actually temperature difference, okay, right. So that's a 1 over t to the power 5, okay. Now if the temperature difference is not there, okay, then, you know, like or you know, even if it's there, then the next subleading correction to that, okay, goes like some oscillation divided by t to the power 6 and so on, okay, and so on. So you can kind of, you know, like there's a cos and sine and so on and so forth, okay, and there's a delta dependence. So you can kind of, you know, like already without doing much work, because we didn't do anything, okay, we just kind of made some very rough model, okay, you can kind of start saying very detailed things about it, okay, and it's interesting, and at least it was very surprising to me, okay, when I realized that this is what is happening, that there's a power law, because you would think that this is a random system, it's a random matrix theory, okay, and you would expect that it should just go exponentially, but it doesn't, okay, and it's a power law, and the power is 5. I think, you know, like this is actually, you know, like given that how generic the random matrix is a good approximation for so many chaotic systems, okay, I think this behavior is very generic. So let's try to understand the power law a bit, okay. Eventually you can kind of follow up this power law, and you can say the power law really comes from the 1 over t cube fall off of the g, because eventually you put some gg, okay, so you get 1 over t cube, 1 over t cube, that gives you 1 over t to the power 6, and then you integrate over dt, that gives you 1 over t to the power 5. It's as simple as that, okay. Now you can understand this power law, okay, by basically understanding that this is very related to how the semicircle, okay, ends at the edges, okay, how the edge behavior of the semicircle, how the edge behavior of the density of states works. For example, instead of rho being the semicircle, you can put some power like this, okay, something which has an alpha power, okay. Then what you see, you know, like going through the analysis again, is that the g goes like this power, okay, and the t goes like twice that power, okay, plus 1, okay, and that is the fall off, okay. So the point is that, you know, like so that is the so that is one way to understand. So the basic thing is that this power of 5 comes from the fact that there's a square root kind of density of states near the edge of the semicircle, okay, and if you change that edge behavior, okay, since everything is explicit now, you can kind of change this power law, okay, and that is what it is, and this and you can also do it for a general alpha if you want, okay. So basically that is where this power law comes from, and wherever, so you expect that wherever there's a square root kind of edge, okay, which then, you know, you expect a power law which is 1 over 5, 1 over t to the power 5, you know, like as it approaches equilibrium. There's also another thing you can also look at, you know, the heat conductivity, heat conductance, and that goes like t to the power 1 plus 2 alpha, okay, which for alpha equal to half just comes to t square, okay. So this is also a generic prediction that your thermal conductivity or conductance for quantum mechanical system for this kind of systems goes like temperature square, okay. So this is all fine, okay, very, very simple. Yeah, so are there any questions? So that's all I want to say. It's a very simple model, okay, and you can kind of, you know, like see what happens with this simple model very, 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 very quickly what happens. Yes. Yeah. So basically, you know, like when delta is near 1, okay, what you're doing is that you're kind of forbidding same side transitions, and you're kind of trying to enhance the farther away transitions. In some sense, you know, you're kind of encouraging transition between this edge and that edge, okay, whereas forbidding the transitions near this edge itself, okay, and that's what, you know, if you just think of it as just the physics of the edges, okay, and that is the basic physics. And then what happens is that there's an oscillation, and you can even see the oscillations are like 2 E0, which is roughly the energy gap between this edge and that edge, okay. So that's it, okay. So now we can get more adventurous, and we can ask, okay, so this is fine, can we make some other models, okay, right, okay. So we can make other models. We can kind of, you know, like make a model which is slightly more complicated, okay, and it's more which we call as a conformal model, okay. So a conformal model, so for example, if this term was not there. Okay, so you know, if at 0 temperature, if you just take some 0 temperature conformal kind of theory, and then you know, like, so where you have a power law and you kind of slightly regulate that power law and then do a conformal transformation to make it finite temperature. So this is a kind of thing that governs the 2-point functions in SYK, okay, which is governed by some conformal Schwarzian kind of dynamics at low energies. Then you get this kind of a model. Okay, so this phi naught is just a constant, so there's some constant which is written in some convenient way. Okay, the thing about the g of t is that this g of t by design almost decays exponentially. Okay, unlike RMT where it decayed like 1 by t cube. Okay, this decays exponentially. Okay, with some power, and you can kind of feed that back. Okay, into this model, and then you kind of get what you would naively expect, that the steady state is also approached exponentially. Okay, right. Okay, so that is for conformal model. Okay, actually this conformal model becomes much more simple, and you know, where you know, like, you can kind of understand at the level of density of states and so on what happens. You know, like, if you kind of look at a limit where this m which appears here, okay, is kind of governed, it's kind of like a dimension in the conformal field theory. Okay, 2m is like a dimension which kind of governs the power law at 0 temperature, and then you know, that becomes an exponential fall off, okay, at finite temperature. Okay, and the point is that, you know, like, so you can take this dimension to be very large, you can take the operator to be very heavy in some coordinated way. Then what you can do is that you can kind of actually make this fall off, okay, to be somewhat like a Gaussian, that rather than e to the power minus t, you can make it fall off like e to the power minus t square. Okay, so actually, you know, this g you can just get it by what we call as a Gaussian model. Okay, a Gaussian model is basically where everything is a Gaussian. Okay, which is also kind of, you know, like some simple model you can think of. Let's say the density of states is some Gaussian which is normalized. Okay, and then let's say the f is also a Gaussian. Okay, again I have some term which is which means it's exponential and quadratic in E and E. Okay, where q tilde is a bit like the delta, which kind of controlled you know, like, you know, same side transitions versus, you know, like opposite side transitions. Okay, and the point is that, you know, like, you can take this f and rho and you can kind of calculate the g, and then you will get some g like that. Okay, so in this model also you can calculate various things. Here basically everything is Gaussian. In particular, you know, like, since everything is Gaussian, you can calculate very many things, you know, like, much more exactly even than in RMT. Okay, for example, you know, like, what you get is somewhat very similar in all these models. What you get is that you get like a peak, a surge, then going this thing. Okay, the how it goes into the steady state, okay, might be different. Sometimes it goes exponentially, e to the power minus t, it goes like e to the power minus t square, but it might wiggle a bit. Okay, but other than that, you know, that's a basic behavior, and you see the same behavior in this Gaussian model also. But you can kind of ask, you know, like, what happens to this peak and so on and so forth, and understand it, but I don't have the time for it, so let me just skip it. But the point is that, you know, like, you can kind of understand, you know, like, how it wiggles and what it means that it wiggles and so on. Okay, so here everything is a Gaussian, and you can and your conductance, okay, basically transforms like some 1 by t square times e to the power 1 by t minus 1 by t square. Okay, so this is again a simple model. Okay, so anyway, so there are all these simple models where we can kind of understand what happens. Okay, and how things go. Now I want to kind of, you know, like, in the last few minutes I want to kind of, you know, like, put these kind of simple models together and kind of tell you how when you do for a double scale SYK system, okay, what do you get? So and what we will see, okay, since I might not have time to go through all the details, let me just say in the summary, what we will see is that the double scale SYK model actually has all these regimes. Okay, and it kind of interpolates very nicely between all these toy models. Okay, so this is a thing for double scale SYK. I guess, you know, like, it basically, you know, like, if you take a SYK Hamiltonian and you take x to be some number of p number of fermions, okay, some Majorana fermions. So you have a p fermion interaction Hamiltonian, okay, and then you scale p to infinity, and you take the number of fermions. This flavor, this I1 varies from 1 to n, and also to infinity. So you take some limit where n tends to infinity, p tends to infinity, where p is proportional to square root n. Okay, so this is called as the double scale limit, and then in this double scale limit, actually this SYK model is completely solvable. Okay, I'm not going to tell you how it is solvable, but it is solvable. Okay, and the point is that it is solvable at all energies. The usual SYK model, okay, which is roughly you take some 4 fermion operator or something, where you scale just n to infinity, the single scaling limit is solvable at low energies. You can understand the IR physics of that model, but here you can understand the full energy energy spectrum, and it's completely solved. Okay. Okay, so in that model you can also take some operators. So I want some operators using which I want to couple it. My operators are also some p tilde fermions, okay, put together. Okay, and then yeah, I should say and you take these like these j's to be some just disordered average. Okay, so you have some disordered average Hamiltonian, okay, and then you have some disordered average operators. And the point is that like these operators, 2-point functions are also exactly solved at finite temperature, okay, in the double scale limit. Okay, so that is the basic point. Okay, I will not explain how it's solvable, but the point here is that so the main thing that governs these things is this q, okay, which is basically lambda is e to the power minus p square by n, okay, which roughly tells you like how many fraction of fermions, okay, among the n fermions interact in the SYK Hamiltonian. And then there's a q tilde which tells you about these operators, okay, which kind of roughly tells you the dimensions of these operators. Okay, so what we see is that like what you can look at this exact solution, okay, by these people in these reviews and so on, and you can look at 2 different limits where you can take lambda to infinity, okay, which basically means that p square grows much faster than n. Okay, so there are more fermions, lot of fermions interacting. Okay, whereas like or lambda going to 0, where very few fermions are interacting as you take n to infinity, which is more like SYK, okay, where you have 4 fermions interacting and you take n to infinity. So what you get is that in the lambda going to 0 limit, you basically get Gaussian like physics, okay, which is what you kind of expect. Okay, and if you take the operators to be very heavy, okay, then you get a Gaussian model. Whereas like in lambda going to infinity limit, where there are a lot of fermions interacting, you basically get random matrix theory. Okay, and in general, what we see is that this double scale SYK has in UV, okay, it looks like this conformal model, okay, this SYK like behavior. Whereas like in IR at long times at low temperatures, it looks like RMT like. Okay, so these statements I will kind of justify. This is all about how you solve it, about Pochhammer symbols and so on. This is just to show you that there are explicit expressions in terms of Besseli functions which you can just solve it. Okay. Anyway, so let me just show pictures. Those are better than throwing equations at you. So this is like a density of states, okay, at different q's, and you see that basically like at when there are many fermions interacting, you see some semicircle, okay, and then you kind of reduce it and it kind of broadens it, it peaks, and then it looks more and more like a Gaussian. Okay, that's how the density of states go. Okay, which is basically converting those formulas into pictures. Okay, and similarly, yeah, so this also says somewhat the same thing. So this particular double scale SYK model, so in various limits, actually leads to all these 3 behaviors: random matrix theory, conformal, as well as Gaussian behavior. Basically, at low temperatures, like you get RMT like behavior, whereas at high temperatures you get like conformal like behavior. And then at high temperatures, if you also take the operators that couple to be very heavy, okay, you get Gaussian. Okay, okay, so then we can obtain the heat current and we can kind of justify this. So this kind of tells you that kind of gives you some evidence. So you can take these exact expressions for the heat currents and plot it, and actually like compare it against what happens at small times, okay, in the UV, okay, which is small times high temperatures. Okay, how does it look? Does it and it looks roughly like conformal behavior. Okay, This is for intermediate couplings, by the way. The good thing about this is that even in the intermediate couplings, okay, so at these edges of these couplings, it behaves like this or that, and in intermediate coupling, it kind of runs between this and that. Okay, and this is what it shows. So in intermediate coupling, you have an exact answer, and you can kind of show that in the UV, it behaves like the conformal model, and in the IR, it does behave qualitatively like the RMT model. Okay, in the sense that, you know, like the, you know, where you just numerically put in the exact expressions in terms of these exact solutions of the double scale SY. Okay, so this is another example, okay, where you just look at the thermal conductance. Again, you see that so this is beta, okay, so high temperature, low temperature, and then you again see that, you know, the thermal conductance, its dependence on beta is also very well captured by this idea that in the UV you have this conformal model, and in the infrared you have this RMT like behavior. Okay, okay, so let me kind of summarize. Okay, so what we have done. So the basic idea is to give a solvable model for heat transport, okay, in the double scale limit, and in the double scale SYK is a very nice model because we can calculate all these things, okay, by some set of things that because of the exact solution, okay, in the double scaling limit, and you can use that actually to kind of understand problems like this non-equilibrium heat transport problem, including the transient problem, which is very difficult in ordinary SYK unless you do some unless you solve some Schwinger-Dyson equations or something. Here you are just, you know, plotting some Bessel functions, okay, and then, you know, like and what you see is that this model, this is a sufficiently complicated model, but it kind of shows that, you know, like this model shows that, you know, there's a behavior where, you know, it goes from some conformal kind of behavior in the UV to some random matrix kind of behavior in the IR, and I think this is a kind of hopefully a generic behavior. Of course, it's very difficult to kind of justify unless you have other solvable model, but I think it's probably a very generic behavior with various kind of power laws and how things are going. And those simple models you can just understand, you can just calculate, you know, like, and understand what happens, okay, and you can also understand various scalings for thermal conductance and so on, okay. So then there are other future directions, but I think I'm already out of time, so I will just leave it at that.
We have time for a few questions.
I have many questions, but I'll just ask two. One is there is sometimes this quantum BEMP effect where the farther away you are from equilibrium initially, the faster you approach. Do you see something like that in your case?
Well, yeah, not that we see. So the transients themselves, it seems to be quite insensitive to how apart you are in equilibrium, because it's all about the connecting physics. After that, maybe, yeah, you're asking, you know, like if it saturates to higher currents, okay, does it go faster? Actually, the power laws are pretty generic. I think power laws are just determined by the spectrum. This is what we see.
I think it would be more like how initially falls off after the transient more than the late time.
Yeah,
I'm not sure.
yeah. So how it approaches the steady state seems to be more governed by, you know, like this kind of edge physics. See, the main difference between RMT and this Gaussian and so on and so forth is this edges. The edges are different. You know, like in a Gaussian, it's smooth. Okay, and then you have a sharp edge with some power, and then you get a power law. Okay, and that seems to be governing it rather than how far away you are in equilibrium. Okay, the steady state, whether you reach it exponentially or power law, seems to be more a function of that, the structure of the energy spectrum. Then, yeah.
Another question. I didn't see if in the SYK model you can justify the assumption you made about the form of the matrix elements in the beginning.
Yes. Indeed, we justify it in a paper. Sorry, I couldn't kind of say, but you can actually, you know, like the matrix elements, the exactly solved double scale SYK, you can look at the matrix elements and you can give an exact mapping. Okay, so this almost cooked up kind of matrix square element from the random matrix theory, all of that you can justify. Okay, and we give these exact mappings in our paper and so on.
Yeah, so I had actually two questions. The first is it or how does one understand this that there is no operator dependence, the coupling H end, because one would think that let's say you took two fermions from one side and two from the other side and just did the SYK thing in coupling, then you would expect exponential profile. So
Well, you don't actually. The point is that long times is governed by more by this RMT like behavior, and you get a 1 over t to the power 5. Okay, it's surprising, but that's what happens in double scale SYK. You cannot see it in the usual SYK, okay, because you can only solve for low energies, okay, and you don't always get the full, you have to probably do some 1 over n corrections or something. But the point is that here it's an exact solution, okay, so you can just look at it and you see that the at long times basically the RMT takes over, because the double scale SYK kind of starts off like SYK, conformal SYK, but in UV, but it kind of runs down to RMT even at intermediate couplings, any Q, okay, and then at long times it is governed by RMT physics, which means that it's governed by 1 by t to the power 5, okay, in its approach. Independent of how you couple the operators and so on. Unless the operator you take the heavy and then you have some Gaussian behavior. Yeah, then you do some other scaling.
so and the other thing I wanted to ask was like the coupling to Schwarzens, should one think of them like coupling to ADS, I mean JD gravities to different temperatures and then looking how they equilibrate and
yeah, so the double scale SYK, like there have been various kind of proposals for what its full gravity dual is. Okay, I didn't want to get into that. Okay, but hopefully one can take these proposals and do it. Okay? So JT gravity of course is the low energy this thing, but this suggests that JT gravity is like, if you think of it as Schwarzian, okay, there's a kind of further IR where you get some RMP. Okay, that's what it suggests, but I don't know, like, I mean, you have to check that what does it mean in the dual holographic description.
We have time for maybe one more question. This one.
A quick one. I mean, do you expect this surge to exist in higher dimensions if you did it? I mean, this symmetrical surge.
Probably so in higher dimensions. I mean, you can. Okay, I haven't done any higher dimension, but if you think of higher dimensions as coupling like a codimension 1 surface, you connect. Probably, I think. Yeah. But yeah, I don't know. Yeah.
Okay, so let's thank Loga for this wonderful talk. Our next speaker is Pramod Padmanabhan. He's going to speak about higher spin integrability using supersymmetry algebras. Show you the card after 20 minutes.
Yeah. Okay, so I want to start by thanking the organizers for actually squeezing me into this schedule, because I was not initially part of the schedule. So at the same time, I want to thank the person who did not show up, and because of which I'm able to give this talk. So I am from IIT here. I'm a local participant, and we're very happy to share the stuff that we have been doing here. Yeah, so I first want to acknowledge my co-authors in these works. So Somnath, who's probably over here, he's my PhD student here, and Vladimir, who's in Stony Brook in the C and Yang Institute, and Jarmo Hitarinta, who's a senior person in Finland. Okay, so I'm basically going to solve this equation, the Yang-Baxter equation. So we have already heard a talk like this by Shailesh in the earlier part of this meeting. However, so Shailesh was trying to show you the fact that like this is not an easy equation to solve. Of course, the equation has not changed, but I'm going to try and impress upon you the fact that it is not so hard to solve this equation. Okay, wait, I press only this button and this button. Yeah, the pointer. So maybe setting something else. No, it happened in the
यूनिटी खराब हुआ है ना, यही वाला खराब हुआ है। हम फिर स्पेसिफिकली किसका
यहाँ से मान लिया वगैरह करना हुआ तब तक यहाँ से एडिटर वगैरह करना हुआ कीबोर्ड वगैरह नहीं है ना, कीबोर्ड है कीबोर्ड
चाहिए। अभी लाइव हो रहा है, लाइव हो रहा है, लाइव बंद कर दिया, हो रहा है। बस इसी का टॉक लाइव नहीं हो पाया ना, बाकी सब अभी फिर से लाइव चालू हो गया। वो आए, दिशा रंजन आए। नहीं, दो प्रोजेक्ट काम नहीं कर रहे थे।
Follow.
Okay, so we'll reconvene. So in this session, we'll have 3 talks, and Professor Pramod Sukla's talk, we'll just shift it after lunch. Okay, so the first talk is deform safety and 2D in ADS. So that's by Suchetandas.
So, first of all, thanks to the organizer for inviting me in this amazing conferences, and also I'd like to thank the many speakers and many amazing talks, which actually helps me to clarify some of my works. And okay, so let me begin. So this talk is based on these 2 papers. Mostly in the first paper is I wrote with Anirban. Anirban is a postdoc at Ningbo University in China, and another is the single author paper. And okay, so this is the brief plan of my talk. So first I just introduce this, what is mean by this deformed CFT, and then what is the connection of 2-dimensional ADS and this effective classical theory and deformed CFTs, and the last part is about some comments on 2-dimensional de Sitter and deformed CFT. So first I will introduce what is deformed CFTs. So first, as if the name is just like slightly misleading, but actually it is not a deformed symmetry. Means not we are not deforming the conformal symmetry. It is actually what we are considering is just SL2 or deformed CFT Hamiltonians on a strip or on a cylinder. Okay. So this means that like so we are actually deforming the stress tensor of the CFT with some specially inhomogeneous function, just like in this. Can I point with this pointer? Okay. So just like this cos x, sin x, these are the some special inhomogeneity, and it affects this the stress tensor. But still, the point is that even if we this deform this Hamiltonian in this way, such that it can be written in terms of some SL2R generators like L0, L1, L-1, which is the SL2R CFT generators. So, and the important point is that the full conformal symmetry is still there. It is not broken or something. But we are just, it is deformed, the Hamiltonian is deformed in such a way. So, just exactly, yeah. That's speciality. Yes, yes. That is it, but yeah, so there is a very special thing. And it is the most general, most general form of the Hamiltonian, which is Hermitian, using in the SL2 form. So, and you can see that this left hand side is the cylinder, the Hamiltonian in the cylinder, and the right hand side it can be mapped in the complex vector. So, and as I am saying that it is still the conformal symmetry is not broken, because if we the Hamiltonian acting on the conformal vacuum of the SL2C invariant vacuum is still it gives 0. So it annihilates the vacuum. So it is the conformal symmetry is still there. Another way we can consider the SL2 deformed CFT on a strip. For instance, you can use the same form but on a strip, not in a full cylinder, and it can be mapped to the upper half plane by conformal transformation, and where this the boundary of the upper half plane is z equal to z bar. So here there you have to satisfy this conformal boundary condition. But one point is that this part is still preserves this SL2R invariant vacuum, but not this part. This part actually doesn't preserve this. So this breaks the boundary condition in some way, because you can explicitly check this, that it does not make invariant this upper plane of the boundary. Okay. So now one question is that how can we construct this deformed Hamiltonian made naturally? So there is one thing so it comes from in the literature previously in the context of this Fouquet CFT or periodically different CFT. So this gives a natural setup where we can have such type of Hamiltonians very naturally. So for instance, like so what is periodical different CFT? So suppose we consider some initial state psi naught, and then you periodically drive the system for some Hamiltonian H1 with for time interval tau 1, and then by some Hamiltonian H0 for time interval tau 0, and then periodically repeated this. Okay. So now you'll get some sort of out of equilibrium system, right? Because you can just drive with the system by changing the Hamiltonian periodically. But the same system, same setup can be written in terms of time independent way, which is called the Fouquet Hamiltonian. So it is a time dependent Hamiltonian system, but it can write in a Fouquet Hamiltonian, which is time independent, with a time t, which is called the stroboscopic time, or the number of drive. It depends on the number of drive. So this Fouquet time is the stroboscopic time, which is proportional to the number of drive, and it gives a time independent setup. Okay. So we may think that this HF actually this so H0, H1 is any SL2R generators we can consider, and HF is either HC or HO, and like which we defined earlier that on the cylinder strip, and it generates stroboscopic time. So it has many features in the Fouquet CFT. One of the features is that it has many dynamical phases. Okay, like it contains 3 types of phases. Like one is like One is called heating phase, one is called the non-heating phase, and these two phases are separated by a phase boundary. So it is determined by this. So this alpha beta actually defined earlier. This alpha beta and gamma. So it provides a certain Casimir of the SL2 Casimir, and depending on the sign of the Casimir, you can define different phases. So one is the heating, and so it has defined signature of these phases. And so one of the important phase is the heating phase, and it features like it has some spatial fixed point of the flow. This means that some spatial point where the flow becomes stopped, or I mean it does not flow further. So this is the fixed point of the flow. So one example of the heating phase is the modular Hamiltonian in safety vacuum. So I'll come to that. So what is modular Hamiltonian? We know that this modular Hamiltonian on a ring, or modular Hamiltonian, I have not said that it is just the reduced density matrix. You can write any reduced density matrix as a e to the power minus HM, and that is HM is the modular Hamiltonian for a subregion. And for its half of the ring, you can write it is as a the modular Hamiltonian can be written in terms of this L1 plus L minus 1 and L1 bar plus L minus 1 bar. So it is already, we have seen this previously. This is the form of HC in this. And modular flow, it actually just so it generates an automorphism of algebra of operators. It means that any you take any algebra of operators for a subregion A, and under this flow, it generates an automorphism. I mean, it gives the same algebra. So it takes you to the same algebra with some state, what is spatial state, which is called cyclic and separating, and it gives a thermal notion because it satisfies some any 2-point function in the state satisfies KMS conditions. So I'll describe something called modular quantization. So this is a notion. So we give this name, that it means that we have to quantize the CFT in a modular time. Not in, it is just different from the radial quantization. Radial quantization is a radial direction is the time, but here we are quantizing in the modular time. So modular time is something that so that just like Riller, in the Riller question, the Riller time is the modular time. So similarly here we are quantizing the CFT in the modular time, and so it gives a map from the complex plane to the new plane, which is from Z to the omega. Omega is a new plane. So omega is just basically S plus I theta, and S minus omega bar is S minus I theta. S is the time, is the modular time, and Z bar is the plane complex plane coordinates. So there are some important features of the modular quantization. One is that it has some Euclidean time circle, and it has still a non-complex spatial coordinate. So, and it also has fixed points, and as I have already described that, and the spatial fixed points is located at Z equal to plus minus I, on which is in the theta omega coordinate. It is just theta is just plus minus infinity, the end points of and it is in the original setup, it is just the end point of the interval. So just like it is a fixed point of the modular. Yeah.
So this HM is the Hamiltonian of the drive. And what is this modular flow doing?
No, HM is the Floquet Hamiltonian, you can say, but it is
Is the Floquet Hamiltonian of the is a Floquet is a modular.
Yes, yes.
So you're evolving with this thing, but what is K psi now?
No, K. Sorry, actually, yeah. So actually, this K is actually this thing. Actually, I mean, I just lied it this way, but K is actually the HM.
Okay,
So,
this is why I got confused.
Yeah, sorry.
Yeah, and
Psi is just the vacuum, because we are the vacuum is the KM state now, because we are evolving it is a modular Hamiltonian with respect to the safety vacuum of a subregion A, or that is the half of the ring, you can say. So it is the form of this. It is already known in the literature.
yeah, okay. No, I got confused because K psi.
No, sorry. Yeah. It is the same thing.
I see. And what do you mean by the modular frame here? Why this?
So it is same means that when we are quantizing this thing, so we are suppose we are quantizing this this time is the flow generates the time S. So equivalently we can say that the complex plane we can map to the new plane. That is the modular plane where the time is the s. So theta is from the. I mean, we can derive this just from the
Oh, I see.
curve equations. From
I
the,
see. I see. So it's a conformal map that
Exactly,
you are
exactly, conformal
generating
map.
by the. Okay. Thank you.
Yeah.
Thank you.
Yeah, so and another important point is that at the fixed point there is a emergence of conformal boundary condition, but in the new omega plane, not in the z plane, but in the omega plane, you can see that we can there is a conformal boundary condition that is emergent due to this fixed point, and we can need a cutoff to impose this conformal boundary condition at theta equal to plus minus lambda. Lambda is the higher cutoff, you can say. And also there is an important thing that there is an emergent Bhubaneswar algebra. After imposing the cutoff, you can actually get an emergent. You can get a new Bhubaneswar algebra that is not the actual Bhubaneswar algebra of the theory of the CFT, but it comes from, if you suppose here H is L0 plus L0 bar. So this curly L0 is just L1 plus L minus 1. This L1 plus L minus 1, and L0 bar is just L1 bar plus L minus 1 bar. And if you consider all the modes of this H, these are like L, K prime, Bhubaneswar modes, and this actually it generates a Bhubaneswar algebra. You can show that there is a beautiful work by Tada, Isibashi, and so on. And so and the point is that this there is the central charge is now it becomes an effective central charge, which is not just C but C into lambda. Lambda is cutoff. So this effective central charge is just a new central charge coming. And also another feature is that I have observed that there is a degenerate vacuum sector of this modular Hamiltonian, and this vacuum sector is just the primary fields at the fixed point ZF. So this fixed point, I mean, some primary fields at O at Z or O at I plus minus I is the acting on some vacuum, conformal vacuum, is the degenerate vacuum sector of this modular Hamiltonian. But however, these are disappear in theta goes to plus minus infinity. If you just map it to the omega plane, these vacuum sectors are disappear. Okay. So now I will come to this uplifting to this CFT we have constructed, and now I will uplift it to the ADS3. So we know in ADS3 CFT2 that there is a large diffeomorphism. It is generated by the boundary conformal transformation. And another important thing is that this boundary modular flow is bulk modular flow. It is an important relation by JLMS, so Japanese Leukovic Morgason and so. So they show that this any boundary subregion, the modular flow is encoded in the bulk subregion small b, which is called the entanglement OH, and so these two are identified up to order Gn. So now the question is that we can so using this map, using this Z equal to tan omega and Z bar equal to tan omega bar, we can actually uplift the modular frame to the ADS3, and this gives actually an ADS and this gives a metric which is the ADS Wheeler, which is of this form, and this R has the range is 1 to infinity. 1 is the horizon of this ADS Wheeler and infinity is the boundary, and theta we can use a cutoff because theta is actually minus infinity to plus infinity, but as I have already argued that we have to put a cutoff at the fixed point, so we have to put a cutoff theta is minus lambda to plus lambda. So now this modular quantization as well as this JLMS relation, actually from that it is like suggested that whether we can quantize the fields in the ADS Wheeler, then we have to put a stretched horizon at the horizon, near the horizon, because the theta is lambda is actually mapped to the horizon of the ADS Wheeler. So we have to put some whether we have to put some stretched horizon in the ADS Wheeler to quantize this system in the bulk. So one check for this proposal is that we can, if we compute the ADS Wheeler entropy with the boundary cutoff, it gives a finite entropy because we have put a cutoff at the boundary, and it is same as the thermal entropy of modular quantized CFT using from the annulus partition function. So if we compute this modular quantization, and if we compute the thermal entropy of from the partition function, it gives the same entropy from the annulus partition function, and it is same as the entanglement entropy by definition because there is a modular Hamiltonian. So the entropy is gives the entanglement entropy, and both of these are same, and it gives this expression. So this is gives the c by 3 log 2 is just the actually 2 RH by epsilon. RH is just 1, so it is 2 by epsilon plus 2 and SB1 and SB2, and these are the boundary entropies. Okay, so this at epsilon goes to 0 limit, these actually mostly contribute. So these are actually, so I'll come to that later. But so holographic safety. So for a holographic safety, this suggests that if we take this C effective, so C effective means C into lambda. So if we take C effective goes to infinity limit. So for holographic safety, this means we have to take C goes to infinity limit first, because by definition the holographic safety has the last central judge limit, which gives the the ADS3 with gravity limit in ADS3 with a fixed lambda, and it gives the ADS Wheeler with a fixed boundary lambda at Gn goes to 0 limit. So this gives a holographic safety meaning of this. Now another limit you can take from this thing, that is that this is C lambda is just C effective. So whether the same C effective goes to infinity limit, we can impose, but suppose for our case C equal to order 1, this is non-holographic safety, C equal to order 1, but lambda is infinity. So, and we still get the same entropy, but question is that what is the meaning of this thing? What is the interpretation of this new limit? I mean, it is not, so we want to understand what is the meaning of this limit. Okay, so now come to two-dimension ADS. So, so first I will discuss this reduction to ADS2 and what is and its connection to jetty gravity. So, like pure Einstein gravity is negative cosmological constant in 3 dimensions, and if you consider a class of asymptotically ADS symmetric with this form, where phi is the dilaton fields, and theta is some cutoff as the boundary cutoff minus lambda to lambda. It is not a SF reduction, but a linear reduction, but with a cutoff. Then we get the 2D effective theory is just a pure jetty gravity, and up to a boundary given something of so this GHY term, it is well known that this boundary term actually captures this time repermutation symmetry and its spontaneous breaking. So, and it is this breaking is captured by the Schwarzian term. So this Schwarzian term is a Isildur invariant term, but it still breaks the time repermutation invariance of the asymptotic symmetries of the ADS2. So now this dilaton boundary condition. So to get this Schwarzian term, we have to impose a dilaton boundary condition on the dilaton field phi. So, and this is given by this pi r by epsilon. This pi r is the constant. To get this Schwarzian term, actually it is given by this paper. So, but for ADS Wheeler gauge, we know this pi r is proportional to lambda. So it is a boundary cutoff. And so already from this type of metric, which is the asymptotic ADS metric, if we write it in terms of Graham gauge, then this near boundary expansion of this gauge already told us that the dilaton boundary condition is the, because you can identify this phi as the r for the ADS Wheeler case. So r goes to, at the boundary limit we can put a cutoff at the r, which is some r by, I mean some lambda by epsilon or something. So already this Paperman-Graham near boundary expansion already gives the UV input dilaton boundary condition. So from this case, in the 3D gravity non-extremal case, we know that ADS safety secretly knows about jetty gravity, at least this setup. And so, and ADS safety tells us that that this for purely pure gravity in the bulk in ADS3, so that is dual to the some stress tension sector of largely holographic safety, because like there is no other field in the bulk, so the only possibility is the stress tension sector in the largely holographic safety dual. So the question is that how holographic largely safety encodes jetty gravity. So like stress tensor sector. So it is just from the, I mean, the same logic. It shows that it must be somewhere in the safety sector in the yeah. So, and we have shown that this Isildur invariant Schwarzian action is obtained by okay, so there are some clues. So that this since the Schwarzian is Isildur invariant and It is obtained the boundary proper time frame, which is called the UV time frame. And the Schwarzian equation of motion gives the Schwarzian term is to be constant, and where f of s is the time determination mode. So the question is that from all this data, what is the UV Hamiltonian? Can we consider the UV Hamiltonian, which generates the time s, this time this time determination? Yes. So our claim is that this holographic CFT with stress tensor sector with SL2 or deformed Hamiltonians may be dual to this jetty gravity in this area safety language, because suppose we know this H, this as we have already said, that is H can be written as alpha L0 plus beta L1 plus L minus 1, and it contains three possible class. One is ADS to Poincare, black hole, and global. So because this Hamiltonian is a deformed CFT, it can be written as a CFT on a curved background. So this curved background is ADS to Poincare, black hole, and global. Sorry. So we have checked that this time generated by these deformed Hamiltonians is the UV time of the ADS to black hole, Poincare, and global for these three classes. And also it provides a constant Happonen stress tensor sector or the Schwarzian term. And one-sided jetty from half reduction of the ADS cylinder, we can essentially match of this jetty density of state to the same modular quantized Hilbert space, the density of state of the modular quantized Hilbert space with C goes to infinity limit. And we can also compute the entropy, and we can match it from the both sides. So, and also there is that this maximal Lyapunov of growth we have already seen in our previous papers, that just like Schwarzian also captures the maximal Lyapunov of growth. So similarly, this deformed Hamiltonians in the heating phase, like for when this gives the black hole, it is black hole, then it gives the maximum Lyapunov of growth. And okay, so the UV frame, that is already we have seen the proper boundary time frame of the this jetty gravity. So this can be written as the ADS cylinder with a boundary cutoff, or the holographic safety to in ADS to black hole with a fixed stage horizon background, because this lambda here is actually the stage horizon in the dual safety, and all it is equivalent to half-sided pure jetty gravity from the half reduction of the Einstein pure Einstein gravity. So now I'll come to the another reduction, which is to ADS2 from and mass speed relator. So like ADS2 because H2 is obtained from near horizon. ADS2 because H2 is obtained just on the extremal limit of the in the near horizon sector of the black on any higher dimensional black holes, like TAD or ADS black holes, and ADS2 in Poincare can be obtained by taking first extremal limit and then near horizon limit, or you can take, if you just take the first near extremal limit and then the near horizon limit, you can get this ADS2 linear coordinate, the ADS2 in black hole coordinates. So the effective theory in near horizon near extremal limit, this actually becomes the jetty gravity plus a topological term. Okay. So it is already described by this beautiful paper by Trivedi, Ashish, Ronak, and others. And the crucial point behind this reduction is the use of a particular well rescaling factor of two-dimensional metric. Okay, so there is a 4D metric we can start, and then we can reduce in the 2D metric, and we have to well rescale this 2D metric to get this type of jetty gravity. So now, so the question is that if we choose a different scaling factor, different well rescaling factor, and fixing the dimensional reduced ADS2 background, then we can actually see that we can get this free massless dilatons up to a GHY boundary term in the ADS2 black hole background, or in a ADS2 background. Okay. So like free massless scalars in a rigid ADS2, it gives a non-normalizable constant solution at asymptotic infinity. So it has both normalizable mode and non-normalizable mode. But non-normalizable mode, we can think of this as a source of the time deformation symmetry breaking Schwarzian action. So from this case, this source of this dilaton boundary condition automatically appears. And so the classical action it gives that this massless free dilaton is constant Schwarzian term in ADS black hole. So this is the classical actions, and okay. So and we are we would like to connect this with the modular quantization in another limit that we have already imposed that. So the first of all, this Hamiltonian can be written in this form. Here this d theta t naught, this is the just the Hamiltonian of the CFT or the c equal to 1 CFT or the massless free dilatons on this ADS to black hole black term plus a constant Schwarzian term which is from the Schwarzian sector. So this Hamiltonian itself is written in the sum of these two terms with Schwarzian to be constant, yeah. And so for c equal to 1, this lambda actually plays the role of this new effective gravitational constant. So it is between Newton constant with phi r by Gn. Phi r is the Gn constant. So semi-classical limit you can think as that phi r goes to infinity since it is an effective Newton constant. So either you can get phi r goes to infinity limit is same as the Gn goes to 0 limit. You can either this thing or this thing. So exact match. So as we have already argued previously that this we can take another limit where with c equal to 1 but lambda goes to infinity, and this is actually plays the role by phi r goes to infinity limit. The exact matching of this entropy at JT density of state for this setup we have already seen, and the question is that what about the emergent boundary state in the lambda goes to infinity limit? Because like already we have put a state horizon cutoff with some boundary condition, but when we but the question is that when we take this limit like lambda goes to infinity, means the space horizon goes to the nearer to the horizon. So whether this what about the boundary state, because physically we don't expect there should be a boundary state still there, but neither it seems that the conformal boundary condition will still be there in the above limit. However, the only states emerging in this by this taking this the same limit are the primaries at the fixed points, and we can see that, as we have already mentioned earlier, that these primaries are actually disappearing when we map from the in the proper time frame or in the ADS to black hole. So only conformal vacuum only survives. So all the SL2 infinite vacuum only survives. So and one can check that this for this case that boundary entropies are vanishing in this limit. So the total entropy is just the integral entropy plus the boundary entropy, but the boundary entropies are already vanishing in this limit. So these already suggested that this space horizon with some emergent conformal boundary space may be the kind of real UV input, which is consistent with the emergent bulk electric field theory. Like because at the sun goes to 0 limit, this boundary condition somehow be vanishing at somewhere, and we have all the what we expect as the bulk electric field theory with a smooth horizon we can get from this. Okay, so and I have just go through quickly that. So because one thing is just I am very ignorant of this physics, so the present discussion could be potentially wrong, but I have some observation which I would like to convey. So for instance, like we know that this near Naria, there is a limit of the Schwarzschild de Sitter black holes. It's called the near Naria limit, which is described by the de Sitter 2 plus H2, and this de Sitter 2 is described by an extended static patch enclosed by black hole and cosmological horizon at the same temperature. And the effective classical action can be obtained as JT gravity with vanishing near Naria entropy, because unlike the ADS case, there is a non-vanishing entropy, near extremal entropy, but here somehow in this de Sitter case, the near extremal entropy of the JT gravity is vanishing because it will cancel the cosmological horizon term and the black hole horizon term. So in the inequivalent reduction, sorry, it is actually so it is a well equivalent reduction, but inequivalent I mean non-well invariant reduction, but well equivalent reduction. So we can get the theory as a massless free dilatons on the same static patch with boundary term in the absence of a GSY term. So suppose because it is a closed universe, I don't know how to put a GSY term in this way, but if we ignore this GSY term, we still get some boundary, as usual we get some boundary term, and the action is that up to this boundary term, the action is just the massless free dilatons in the same static patch which is enclosed by black hole cosmological horizon. So using certain UV boundary condition dilatons at the staged horizon, these boundary terms will be cancelled and one compute the partition function and thermal entropy consequently, and so it can be consistent with the generalized entropy version which is given by this CLPW paper, that the total entropy should be the Naria entropy plus the near extremal entropy, and it is not vanishing there. And pure Einstein gravity in de Sitter also can be directionally reduced to the effective theory on dilatons in the past Milne patch, or then also you can process, but it is shown in the past middle difference, which is actually the in the Sandeep's talk. It is he shows the diagram. It is the upper middle level actually. So and we can see that the effective theory has some potential term and kinetic term. The potential dominates at the initial time, which is like the singular point or something called. I mean, there's some name just like Bhubaneswar, but this is a quadrant singularity. There is a potential time dominance, and at the pure kinetic term dominance at the late time, which is near the I plus. So the question is that can we, from this effective action, can we mimic some? Can we construct some similar to ADS to some CFT Hamiltonian that could mimic these things? So one thing is that if we just construct this Hamiltonian, I gamma L1 minus L minus 1, then you can on a cylinder, it still belongs to the heating phase, and you can see that it has some interesting features. One feature is that upon mapping to the proper time frame, it has a role reversal of equivalent space time. So like in the ADS2 case, it is like some function of S plus I theta, but for this Hamiltonian, it gives theta plus IS. So it is only S and theta just role reversed in this way. And there is a thermal time circle, and all the other features are just same as the modular quantization, but the contour is just the pi by 2 rotated. And except so one thing is the troubling is that there is a negative stress tensor in conformal vacuum. Like maybe so as Sandeep was commenting in his talk that there could be some problem of I in the stress tensor because of this. If we properly encounter this L2IL, I mean this LADS to ILDS, so there could be some crazy thing maybe happens. But in this, what I have done, I have not taken this into account because I mean I think that like in 2D, like physical quantities including causal structure still remain unchanged with fixed signature, because if we don't incorporate this thing, the 2D metric is still just with a plus minus to minus plus signature. So it is still it may have physical things, but there is a negative space. So maybe there is something interesting. And effective dynamical dilettantes. So another question is that how can we construct this past Mendeleev's dynamics, dilettante dynamics? So and it is similar to the critical quench problem, sudden quench problem, because it starts with some potential dominance, which is you can think as some I mean some gap theory, and then it is just going to the gapless safety at the late time. So it is like a critical quench problem, and we can see that this H naught with the same Hamiltonian on the strip is shown to be similar to the serial Cardian quench problem, which is described by Cardian Calabresi, but it has some certain difference from them. But we can see that the evolution of strip vacuum under conformal boundary condition breaking H naught. So this, as I have already mentioned, that this Hamiltonian breaks the conformal boundary condition because it is not it does not preserve the SL2 invariance vacuum, and it gives a non-equilibrium state. But at the late time, we can see that the steady state emerges, and as in Logas talk, it is just like conformal steady state, like it is exponentially in time to reach to the steady state. So thus we can see that conformal vacuum with certain deformed Hamiltonian strip and cylinder, it mimics up to an overall metric signature the pure and black hole de Sitter dilettante fluids in 2 dimension. And there's some future direction I can say. I can just stop here, and I'll not describe now. But there's one acknowledgement I should thank this Bobby for this past. He has very crucial thing he has pointed out in the past paper, and thank you.
Time for a few quick questions.
Can you go to that slide where you talked about entanglement entropy is equal to thermal entropy, like when it appeared for the first time? Yeah. I guess this C lambda by 12 is the vacuum energy of the ADS, right? and the left hand side is an entropy.
Yeah,
so
yeah.
how
So I'm
are-
saying that this, sorry, this lambda is basically this log 2 by epsilon. So I can just write it as, since at the epsilon goes to 0 limit, you can ignore this term, as I'll show later that this actually goes to 0 actually, because when this boundary entropy actually vanishes. So only the dominant part is this thing, and this thing, this lambda is basically, we can I mean match it with the this log 2 by epsilon for this safety equation. So this is the cutoff of the theta, and that can be written as in the r coordinate. It is just like log 2. I mean, in some coordinate, it's just log 2 by epsilon. So the same.
is this just
epsilon-
energy equality instead of entropy equality, like
No, it is just a cutoff equality, because the cutoff it is a redefinition of the cutoff. Epsilon I have not defined. Sorry, I have not defined the epsilon, but it is just the epsilon is related to lambda by this definition.
Okay. If there are no other questions, let's thank the speaker again. So our next speaker is Mazumi Honda. So you have 30 minutes.
Can I start? Can you hear me? Okay. Thank you. First of all, thank you for introduction and invitation. It's always pleasure to come back to India. I'm Masazumi Honda from Weekend Items and Saitama University. Today, I will talk about Picard recess theory and gravitation path integral. This talk is based on collaborations with Hiroki Matsui, Kota Numajiri, Kazumasa Okabayashi, and Takahiro Terada. So let me start with introduction and summary. Focus of this talk is path integral for gravity. And when we consider path integral of gravity, we usually consider Lorentzian path integral or Euclidean path integral. And Lorentzian path integral is conventionally given by this integral of exponential is. And this is conceptually similar, more or less conceptually similar, but of course we know that it's highly oscillating, so it's technically awkward. And therefore, the integral can be only conditionally convergent rather than absolutely convergent at most. And in quantum field theory, we also consider Euclidean path integral, and this is formally given by exponential minus s. And in quantum field theory, since action is usually bounded from below, so it's technically better object since we have a better convergence. So when it's convergent, we have absolute convergence. However, for the case of gravity, action is unbound typically. So naively, we have a worse convergence, or we are not sure even if there is convergence. Of course, this is also related to problem of imposing cutoff. But we also know that at least semi-classically, we know there are interesting physics like black holes, Hawking, wave function, and so on. Here, I'd like to ask two questions. So first question is whether there is a connection between Lorentzian path integral and the Euclidean path integral, or connection between Lorentzian spacetime and Euclidean spacetime. And another question is that what saddles in the path integral do contribute to the gravitation path integral, or we can say contribution to universe. And the message of my talk is that a mathematical tool called Picard's recess theory seems useful to answer these questions, at least partially. Okay, let me explain what Picard recess theory is. We need only ordinary one-dimensional integral to explain this. So suppose we have a one-dimensional integral along some contour. Then under some conditions, Picard's theory gives the decomposition of the integral in terms of saddle point. So here, xs is a saddle point, and the jxs is called steepest descent or recess symbol associated with each saddle point. And note that this is not approximation. So this is the exact equality. And here, nxs determines whether this contributes or not, the saddle points contributes or not. This can be 0 or non-zero. So if this is 0, the xs is not contributing saddle point. And important mathematical point is that this saddle point is generically not on original contour or generically complex saddle point. And appropriately, we are not sure whether this contributes. But the Picard's theory gives whether complex saddle points contribute or not. And here, I'd like to apply this theory, this method to Lorentzian path integral for gravity. Then there is a possibility that some Euclidean spacetime. So we have a Euclidean spacetime might contribute to the Lorentzian path integral as a complex saddle point. So since when we consider this kind of thing, we also consider integral over complex spacetime. So let us consider this approach. And this idea itself is not our original idea. There is already application by Neil Trock and collaborators to a toy model of gravitational path integral, which is called the deterministic superspace model. But somehow previous analyzed one done at the parameter region called Stokes line. This is connected to Stokes phenomena. By Stokes line, I mean that the parameter region where a form of asymptotic expansion or perturbative series is jumped. And this was the, in my understanding, this was the historically first studied by Stokes in studying spectrum of rainbows. And Stokes found that this is given by Airy function. And you know that the Airy function behaves like exponential damping or oscillation depending on the argument of parameter, argument phase of argument. And so this is connected to Stokes phenomena. And it is also known that at Stokes line, the composition in terms of the recess symbol is ambiguous. And therefore, we cannot use the powerfulness of Picard's theory at Stokes line, exactly at Stokes line. So here we take the following strategy. So physically, of course, H bar is real and positive, but we first deform H bar to complex value. Then apply Picard's theory here. And here, for non-zero theta, we found that there is no Stokes phenomena, but we try to come back to the original H bar, original real positive region. So this is our strategy, but taking the limit is sometimes straightforward and sometimes subtle. Actually, we found that for some parameter region, the coefficients of the recess symbol decomposition had jumped. Yeah, usual Planck constant. Yeah. We can also say replace in terms of Newton constant. Yeah. And sometimes we found there is a jump. Then apparently there is a discontinuity in the answer, or this gives the ambiguity of the decomposition in terms of recess symbol. But there is also a mathematical tool called resurgence, and if we use a technique of resurgence, we can also show that this ambiguity or this jump is cancelled from another jump coming from resummation of quantum gravity correction. So this is one thing. And another question is closely related to controversy on beginning of the universe. So second question was what stars do contribute to the universe? And there are two famous proposals. So first one is maybe you are familiar with the non-boundary proposal or Hartle-Hawking proposal. So here the proposal is saying that the wave function, claiming that the wave function of the universe is sum of compact equilibrium. And there is also a tunneling proposal by Vilenkin. And roughly speaking, this proposal claims that the expanding universe was born by a tunneling. And this picture is based on Euler-Dwight equation. So you may know that the Euler-Dwight equation is equivalent to a Schrödinger equation with some potential like this. Then in terms of this picture, he proposed that expanding universe appears from the tunneling from here to here. And here, by using Lipschitz symbol analysis of Picard-Lipschitz theory, we conclude that only tunneling saddle points contribute in the mini-superspace model, unless we identify integral control for lapse function very complicated way. So this is our conclusion. And this picture was one for, so I made a press release for our work, and for this is a picture for used for press release. And this time I asked some professional illustrator to write the picture. And I didn't tell him that Stokes phenomena is was first studied by studying rainbow, but somehow he drew the rainbow. So I don't know whether he knows about the connection between rainbow and the Stokes, our work. And I'm not sure about this right seems to express resurgence, but I'm not sure. Okay, so I finished the introduction and summary. So next I will explain details. So how much do I have? 15, okay, thanks. Yeah. Okay, so first let me explain a setup. So this is four-dimensional action of four-dimensional Einstein gravity. And so we don't study full Einstein gravity. So instead we consider a model. It's based on a very simple ansatz like isotropic ansatz. And then just by substituting this, we have this action. And digital mini-superspace model set this as a starting point. So therefore, this is a model. But people expect that this model gives some approximation of the original problem in something. Okay, so here this is the starting point, and let us consider path integral over lapse function and Q and scale factor. And after some calculation in some gauge n dot equals 0, then transition amplitude is given by finally ordinary integral. So we perform people perform the path integral over Q with the Dirichlet boundary condition. So here we took a Dirichlet boundary condition where the size is Qi at t equals 0 and the size is Qf at t equals 1. So this is finally ordinary integral, then and x is connected to n by n equals x squared. And now we have 3 parameters depending on spatial volume, cosmological constant, boundary condition and K is curvature constant. So now problem is just ordinary one-dimensional integral, and let us apply Picard theory to this integral. So this looks simple problem, but we found that this integral has a deep physical meaning. Okay, so now let me explain a bit more details on Picard theory itself, or steepest descent. So let us extend the variable to a complex variable. Then critical point or third point is simply given by this equation. And here is a unique thing. So associated with each critical point or third point, we define Lipschitz symbol or steepest descent as a solution of this differential equation. So here, boundary condition is saying that so we are introducing artificial time, and at some point we are in third point, and there are nice properties of this object. First, we can show that along with Lipschitz symbol, imaginary part of action keep constant. We can easily show this property by using this definition. So derivative is 0. And another property is that the real part of action is monotonically increasing along the Lipschitz symbol. We can again show this by using the definition. And under some condition, it is also known that the integral contour can be decomposed as a superposition of a Lipschitz symbol. And here, the coefficient Ni is an integer, known to be integer, and also this may jump as changing the parameters. And the name Lipschitz symbols come from a tool for sewing, and this is called symbol. But so I have studied Lipschitz symbol for a long time, but I still don't know why this is called symbol. Okay, let me introduce another notion called real symbol. This corresponds to steepest ascent, and only the difference in definition is minus here, minus sign here. And similar to Lipschitz symbol, imaginary part of action is constant along real symbol, but the real part is monotonically decreasing. So then apparently this sounds not useful, but actually this is useful object. So it is known that the coefficients Ni deciding whether third point is contributing or not is given by intersection number between original contour and real symbol. So by drawing the real symbol, so we can see whether Ni is 0 or not. So this is useful too. Okay, now let us apply this method to our toy model. So we have a one-dimensional integral. First, let us compute saddle points. And we have 8 saddle points labeled by plus, minus, and n equals 0, 1, 2, 3. So we have 8 saddle points. So this is explicitly given by this. And here by historical reason, we classify saddle points as false. So if we have a negative real part, we say the saddle point, we call saddle points tunneling type saddle point. And there are also non-boundary saddle points which have a positive real part of F. And so next slide, I will show you Lipschitz symbols for some parameters. And we found that there are 3 parameter regions which have a qualitative difference in from the viewpoint of Lipschitz symbol. And this is divided by okay, there is an inverse here. Yeah. Then saddle point equation becomes like yeah, x is polynomial. Yes, yeah. Okay, thank you. Yeah. The negative guide increases the number of saddle points. Okay, and it turns out that qualitative behavior depends on this combination of parameters, and in terms of physical values, it's given by this. And when initial size is 0, physically we can say that the first region is corresponding to computing transition between Lorentzian spacetime and Lorentzian spacetime. And there is also other regions describing transition between Euclidean to Lorentzian or Euclidean to Euclidean. So we will see the difference. So yes. Yeah. Okay. So now I have a saddle points, and next I will draw if the symbols are associated with all the saddle points. Then I will study a connection between original contour and part of if the symbol. Yeah. Okay. First, let me start with the simplest case, which is supposed to describe transition from Lorentzian spacetime to Lorentzian spacetime. And dots are saddle points. And blue lines are Lipschitz symbols. And red lines are dual symbols or steepest ascent. And the real line is the original contour. So to see which shadows are contributing, so it's convenient to look at the intersection between red line and the original contour. So we have 8 dots, but we see that here only 4 shadows have an intersection with the original interior contour. So therefore, so the interior contour is given decomposed like here, and here. Maybe I should repeat it in this side. So here, and here. And here, we don't have a problem on Stokes line. So without ambiguity, we can say that there are 4 real saddle points contributing to the integral. And the pure imaginary guys are not contributing. So this is the simplest case. And now next, let us consider bit more complicated case, which is supposed to describe the transition from Euclidean spacetime to Lorentzian spacetime. So we have similar figures, but there is a problem in this figure because sometimes there is a Lipschitz symbol crossing 2 saddle points. And when we have this like crossing of multiple saddle points, this is a signal of a Stokes phenomenon, or this is indicating that we are at Stokes line. So there is ambiguity on the interpretation of the decomposition. So therefore, let us deform the setup so that we don't have a Stokes phenomenon, Stokes line. We are not on Stokes line. Then try to come back. Okay. So this is the figure with for complex H bar. And I'm plotting some value of positive theta and negative theta. So now we see that there are no lines which crosses multiple saddle points. So for example, for the left case, so there are 2 two saddles crossing the original integral contour. And sorry, I forgot to say that the black dots corresponding to tunneling saddle points, while the red saddle points corresponding to non-boundary saddle points. So here we see that black dots are contributing saddle points. And this is also the same for the negative theta case on right figure. Yeah, therefore, for non-zero theta, we see that only tunneling saddle, the same saddle points are contributing, and physically this is a tunneling saddle points. And since contributing saddle points are same between positive and negative, so it should be smoother at theta equals 0. So in that sense, original theta equals 0 can be understood as a limit from the both sides, and there is no discontinuity. This guy? This guy? No, sorry, this guy is terminating at the origin. Yeah. That is not intersecting. Yeah. Yeah, so this integral has a kind of a singularity at x equals 0, and that their symbol has a end at the origin. So it's not crossing. Yes. Black one is tunneling saddle, and red ones are Hartle-Hawking or non-boundary. Yeah. Black guys has a negative real part. Yeah, and red one has a positive real part. Okay, and next I'd like to explain the most complicated case in our setup, region 3, which is supposed to describe a transition from Euclidean to Euclidean. So this is for real H bar, real positive H bar. And again, we are in Stokes right. And by the way, this is plotting x, and n equal x is related by n equal x square, and so this line is corresponding to Euclidean spacetime. So again, let us consider complex H bar. So now we have a more complicated figures. So let us focus on left figure. So on left figure, there are four saddle points having intersection, having their symbol intersecting with the real axis. So on left hand side, we have 4 saddles contributing to the integral. But on the other hand, on right figure, where theta is negative, we have the difference. So here, there are only black dots are contributing. So their symbol of red saddle points changes the direction, or direction is sensitive to the sign of theta. So on left hand side, we have 4 contributing saddle points, and on right hand side, we have 2 contributing saddle points. So this is a Stokes jump or Stokes phenomena. So therefore, it seems that we have a jump of the coefficients in the decomposition in terms of recess symbol. And naively, one might ask that, oh, does this mean the transition amplitude is discontinuous at theta equals 0? And actually, for this case, the answer is no. So the resurgence comes to the rescue. So we can show that discontinuity is coming from this guy is minus of the ambiguity coming from the Borel summation of H by expansion around the saddle point. So this is another main result. And so let us briefly explain what happens here for some special parameter. When gamma equals 0, we have this integral, and we have a saddle point here, and around the saddle point x equals 0, we can explicitly compute the perturbative series or H by expansion like this. Then, so I skip what Borel summation is, but Borel transformation is explicitly given by hypergeometric function for this case. And then, so we'd like to do inverse, like Laplace transformation of the Borel transformation. But this guy, Borel transformation, has a branch cut along the positive real axis. Yeah, therefore, naively at theta equals 0, we hit singularity. So this gives the ambiguity at theta equals 0 or real positive H bar. But we confirmed that so up to order H bar to the 100, the ambiguity is coming from Borel summation is exactly the same as minus of the ambiguity is coming from Stokes jump. And we also numerically check that the result is continuous at theta equals 0, but this is a mechanism of getting continuity behind continuity. Yeah. Okay. So let me summarize. So message here is that Picard's theory is useful to answer the question like what is the connection between Lorentzian spacetime and the Euclidean spacetime. And then Euclidean geometry can appear as a complex saddle point in Lorentzian path integral. And another question was what saddles do contribute to the gravitation path integral? And first of all, so if this symbol Picard's theory tells us that this question itself is a generically subtle question, and sometimes this does not have a unique answer due to Stokes phenomenon. But resurgence implies that there can be multiple correct answers related to reformation property of quantum gravity correction. And here, unless we consider complicated contour for lapse function in original setup, then we found that only tunneling saddle seems to contribute in our setup. And there are a lot of questions or a lot of things to do. So first, what happens if we consider beyond the municipal space approximation, or if we include matter or something like that? And also, another natural question is whether our conclusion on contributing saddles are typical or special in generic situation in gravity. And so far, we found that JT gravity has a defined property, explained in next slide, and we are also working on other dimensions. So here finally, let us finishing by briefly mentioning our result for JT gravity. So if we apply again a municipal space approximation for JT gravity with cosmological constant, again we get one-dimensional integral. And if we consider apply a Picard theory, then we get similar plots to parameter region 2 in 3+1 dimensional Einstein gravity case. And again, for this case, we found that only one saddle point is contributing. But this contributing saddle point is not tunneling saddle, but non-boundary saddle. So it seems that for JT gravity in superspace approximation, in contrast, 3+1 dimensional Einstein gravity Hartree-Hawking or non-boundary saddles are contributing saddles. So we are not sure which is more typical or which is special. Okay, this is the end of my talk. Thank you very much.
Questions?
Yes.
Thanks, Masa, for nice talk. So this ambiguity in the border distribution, the jump, isn't this the part of the whole alien calculus framework that this will be the difference in Stokes line? This result, Borel ambiguity equal to Stokes ambiguity, isn't this part of the full framework, alien calculus framework?
Sorry, can you say again?
This statement, Borel ambiguity is equal to Stokes ambiguity. Isn't this part of this full alien calculus framework?
This can be also done by alien calculus, but I didn't use that. Yeah.
I mean, it's a theorem, right?
Yeah. So here, I could show this just by naive comparison. But alien calculus, it should be also available. Yeah.
Other question?
I didn't fully understand your comment about the ambiguity of the measure of the path integral.
Yeah. Good. So, okay, thanks for the question. So this is a very subtle point. So, question is, what is the integral contour? What is the correct integral for Laplace function? And here, we naively took the original integral contour to be real positive axis for n. But there are some other people thinking that this should be whole real line or something like that. So, and actually there is a controversy on this, and since contributing saddle points depending on relation between original contour and their symbol. So if we redefine, if we think if we take original contour to be in different way, contributing saddle points can generally change. Yeah.
I mean, it also depends like what is the setup. For example, you're doing Schwinger-Keldysh versus like in cosmology, often people have to do Schwinger-Keldysh path contour integrals.
Yeah.
So do you think it might be different in that case? Like for example, like real time, like equal time correlations, like people measure in cosmology, requires that you have a finite, go up to finite t, then come back and.
Yeah. It should fully depend on
this.
I see. What starting point is. Yeah.
I see.
Yeah. So here, so our conclusion is that so we did not completely logically exclude Hartree-Hawking, but if we take original contour to be a more complicated way, Hartree-Hawking start point still can contribute. But if we consider, like if we consider naive contour, Hartree-Hawking does not.
Hi. So very here.
Yes.
So very interesting talk. I have just one technical question. When you're talking about this mini superspace model, so practically are you decreasing the degrees of freedom of your original system?
Yes.
So how do you decide that which degrees of freedom are contained and like in the technique that is used, like mini superspace?
Yeah. So. We are not sure. So unless we have a nice definition of quantum gravity, so we cannot have a complete answer. So.
Okay.
Yeah.
Okay, I have one more question. Like in your this Picard's theory, basically this all Euclidean geometry is like a complex saddle.
Yes.
So can all those like phenomena in the Euclidean space, for example, how will you describe, suppose, Hawking-Page phase transition in your Picard setup?
Okay, this is a great question. So I'm not sure about it, but okay, logic is saying that, yeah, so this line is Lorentzian spacetime and this line is Euclidean spacetime. So if there is any physical laws of Euclidean spacetime in Lorentzian gravitational path integral, then there should be maybe some, for example, some contributing saddles along this line, and this may describe, Hawking phase transition, but I'm not sure.
Right? You have to figure you have to figure out which saddle is more dominant.
Oh yeah, this is more closely related to anti-Stokes phenomena rather than Stokes phenomena, but yes. Okay, in that sense, yeah. Okay, for that case, usually we expect that both saddles are contributing, but the dominance is different. Yeah, but even okay, this is discussed in the framework of Euclidean, but in the framework of Lorentzian path integral, first of all, whether both saddle points, so it is non-trivial whether both saddle points are contributing the saddle or not, since they are complex saddle points from a viewpoint of Lorentzian path integral. So I think there are 2 points. Yeah.
Thank you.
Yeah.
Okay, so let's thank the speaker once again.
Thank you.
So our next speaker is Tanya.
Can you hear me? No, no. So I'm audible, right? Right. Good afternoon, everybody. I'll begin by thanking the organizers for giving me the opportunity to present my work here. So today I'll work on rotational Freudenthal duality of black holes in 4 dimensions. This talk is based on these works that I have done with my collaborators Orgo and Alessio. Let me begin by answering the question, what is Freudenthal duality? So we know that duality basically maps to seemingly uncorrelated theories that looks, 2 theories that looks very different, but they are basically equivalent. That's what duality states. For example, electromagnetic dualities, 2D Ising model duality, and there are many more well-known dualities in physics. Freudenthal duality, it relates Freudenthal triple systems with a black hole. It states that originally it stated that 2 extremal non-rotating black holes in asymptotically flat space-time with different charges, they have the same entropy when the charges are related by a nonlinear map. For example, here I denote this Q as the whole dynamic charge vector of the black hole. For example, if I have a black hole with a charge vector Q and another with a Q tilde, if this Q tilde is related to the Q in this following nonlinear way, then they have the same entropy. And here omega is a matrix with this particular property. Now this charge map is anti-involutive, which means that if I apply this particular transformation twice on the charge vector, it gives the negative of the initial charge vector. Now why this particular charge transformation keeps the entropy of a non-rotating extremal black hole invariant? Because for this kind of black hole, if I look at the form of the entropy, they are homogeneous degree to function of the black hole charges, and that basically manifests the idea that under this particular charge transformation, the entropy remains invariant. Okay. So I'll briefly say what is a Freudenthal triple system. It's basically a vector space over some fields. Here, in our case, the fields are real valued. We'll clear that shortly. And it's a vector space such that it has an antisymmetric form and also has a non-zero quadric form delta and a triple product T with this following properties. Now, if all the 4 elements in this quartic form are same, for example, x's are the elements of the this parental triple system vector space, then we denote it as delta x, and we can it's shown that if x goes a transformation like this, x goes to x tilde, then this delta x is remain invariant. This is called parental duality in the original parental triple system. Now, how is this related to the black holes? If we relate the black hole charge vector to the elements of parental triple system and says relate the entropy of a black hole to the quartic invariant of the parental triple system delta x in the following fashion, we see that then the previously mentioned this x goes to x tilde and invariance of delta x under this transformation translates to the following transformation of the charges on the black hole vector or the black hole charge vector, and this transformation of charges gives the entropy of the black holes invariant. So it basically states that for extremal non-rotating black hole in asymptotically flat space time, and anti-involutive parental duality acts on non-linear and the black hole charges, and which keeps the black hole entropy invariant. Okay. It was originally studied for parental duality for black holes, originally studied for non-rotating extremal black holes in asymptotically flat space. That is related the derivative of charge. So it's not that obvious. Okay. So originally it was studied for parental duality, was studied for like non-rotating extremal black holes in asymptotically flat space in ungauged supergravity. Further, it has been extended for gauged supergravity, and also for near extremal black holes in ungauged supergravity. Now, if we remember in some earlier talks in conference, if we remember the form of the entropy of the near extremal black hole. So near extremal black hole means it has some small temperature T, and the temperature enters to the formula of the entropy, and hence the form of the entropy is no more a degree 2 homogeneous function of black hole charges. Thus this way of parental duality definitely does not work or does not hold for a near extremal black hole, but what it states that for them it has been generalized in such a way that two near extremal black holes, when they have different charges related by some nonlinear relation, but also have some different temperatures, they have the same entropy, and that is called some generalized version of parental duality for this near extremal black holes. And it has also been shown that this kind of mapping is unique. Here in this talk, I will discuss this parental duality for rotating black holes. So our focus is extremal rotating black holes in asymptotically flat space. So, and we are basically looking for the black hole solution to the Einstein theory that is coupled to some gauge field and set of scalar fields. So these are the parameters I will need to describe this kind of black holes. So dynamic charge vector Q, angular momentum, and we will discuss both extremal and doubly extremal black hole, and also the part of the entropy. If I just turn off the rotation J here in this kind of rotating black hole, then the non-rotating part of the entropy is not Q, that will also be needed. So it will be clear in a moment. So for doubly extremal black hole, that is the extremal black hole with constant scalar fields, this is the form of the entropy. So if I look at this formula clearly, so if I just turn off this J, say J to 0, this entropy basically becomes the extremal entropy of a non-rotating black holes. And we are also interested in extremal black holes with running stellar. In this case, I have two kinds of black hole, under rotating and over rotating black hole. For under rotating black hole, this is the form of the entropy, when clearly it means like this S naught square, this part is more than this compared to greater compared to this number J square, and for over rotating black hole, when this J square is greater compared to S naught square. Now none of these entropies are homogeneous degree to function of electromagnetic charges. So our goal is to establish a parental duality for, or moreover, like if I say it, say like some kind of invariance we want for the entropy under some nonlinear transformation of charges. Yeah, arbitrary, but just that that should maintain this bound only, that J square is greater than S naught square. Yeah, I think so. Just something that with this bound should be fine. I'm not aware of, okay, I can look at it later. Thanks. Okay, so basically we are looking for some entropy invariance and some nonlinear transformation of charges. Okay. So first, let us begin with the usual formation of a fundamental duality, how that acts on the rotating black hole. So, usual formulation of fundamental duality acts on the charge vector as change the charge vector as follows. So basically, if I just replace this under over this entropy with respect with the extremal entropy is not Q, extremal entropy of a non-rotating black hole. That's how it works for the non-rotating black hole, this fundamental duality. So here I just replace this formula. Instead of S naught, I just use the entropy of the over-rotating or under-rotating or any other than this double extremal black hole's rotating entropy. I just replace that. So that I am calling the usual formulation of fundamental duality. Here this particularly showing for under and over-rotating black hole, and plus and minus sign corresponding to the under and over-rotating black holes here. So now what I demand is that under this charge transformation, the entropy remains same, and this demand asks me to solve this particular equation. Now for an under rotating black hole, we know that this S naught square always greater than J square, which means that this term, this J square minus 2S naught square, always negative. And that means the only possible solution to this equation is J equal to 0. Now J equal to 0 means the black hole I began with, that is already non-rotating, and that we know that for non-rotating extremal black holes the fundamental duality works. So basically it becomes a trivial fundamental duality in our language. Now if I just consider over-rotating black hole, for a over-rotating black hole I know that this J square is always greater than S naught square, which means this J cannot be 0. The only possible solution to this equation is J square equal to 2S naught square. Now if I put back to the this thing to the formula of over-rotating black hole's entropy, I see that the over-rotating black hole's entropy just boiled down to the entropy of a non-rotating one. So basically we see that in both cases for trivial fundamental duality, if I just consider trivial charge transformation under trivial fundamental duality, so both under rotating and over rotating black hole behaves like a non-rotating extremal black hole, and we know that for them the trivial fundamental duality is very obvious. And for doubly extremal black holes also the similar things happens. It boils down to the non-rotating fundamental duality. So these are not things we are then interested. So what we do? We just look for we generalize the definition of fundamental duality for rotating black hole. We just demand that we are looking for two rotating black holes but with different angular momenta. So one has with J and another with J plus delta J, and then demanding that then their charges are related by a nonlinear map, and if this scenario exists with a, if there is two such black hole with the same entropy. So we look for a scenario like this. So how do we say for over or under rotating black hole, we set a charge transformation for them in this following fashion and demand that one rotating black hole with charge q and angular momentum j, and another with a charge q hat defined in the following way and angular momentum j plus delta j, and demand that their entropies are same. Now we are basically looking for these two black holes if they exist. And similarly for doubly extremal black hole also, this is the definition of charge transformation, and demand that under this transformation one double extremal black hole with charge q and j has the same entropy with another one with charge q hat, and angular momentum J plus delta J. Now question is that if there is any such black holes, are there any such black holes that shows this entropy invariance? So we are going to check that. Now in both cases, when we demand this entropy invariance for both extremal and double extremal black holes, this leads us to solve a six-peak equation in delta J. For example, for the extremal one, for both over and rotating black hole, we get the same equation. This is the equation I need to solve for delta J, where these parameters A1 to A7, they are function of angular momentum and the S0 squares. And similar kind of equation also exists for double extremal black holes. So now basically we need to solve this equation for delta J, and this is six-peak equation, but we have checked that both numerically and analytically. Numerically, we can see that only among these 6 solutions, 4 are imaginary solution for delta J. Only 2 delta J are real, and only one of them says that this, which keeps the modified, the second black hole's angular momentum J plus delta J is keeps that positive. So for example, here I show it from a graph. So we analyzed it numerically for a fixed entropy. Only 2 solution of delta J which are real, but on this, for example, delta J1 and delta J2, and among them only delta J2 actually keeps this J plus delta J always positive. So basically there is only one physical solution, meaningful physical solution we have, which keeps J plus delta J always greater than 0. We have also checked it analytically, and this is the form of the solution of for this J hat. J hat is J plus delta J. So we show that this is the form of the J hat square for both over rotating and under rotating black hole, and where this T1 is a function of this again J and S0. Now how does they look? How does this new black hole, this dual black hole looks? To check that, we set a ratio alpha, which is the ratio of J square over S0 square for the mother black hole, and for the dual black hole, we set this J hat square, we set that as proportional to S0 square, and the proportionality factor is some function of alpha called f of alpha. Now using this relation from this expression of J hat square, we can find out the form of this f of alpha, and this f of alpha looks like this. And we can write the dual extremal black hole, extremal entropy of the over and under rotating black hole in this following fashion. So under square, now we are taking the mod out of it. And basically that for both under and over rotating black hole that works, and for the corresponding so RFD stands for rotational fundamental duality. Now for the corresponding RFD dual entropy with a charge vector q hat and angular momentum J plus delta J, this is the form of the way we write their corresponding entropy, but this S0 tilde is a function of S0 and J hat, and ultimately we can write it in terms of the S0 and the function f of alpha. Now we know that for the dual black hole, J hat is their angular momentum, and rest of the part we can think of as their corresponding its non-rotating part. So in the following, just in the comparing this, we can say that when this S0 tilde square more than J hat square, then the RFD dual black hole is under rotating, and when this S0 square tilde S0 tilde square is less than J hat square, then the dual black hole is over rotating. Now we have said some the whole calculation depends on this parameter alpha, and alpha can be any positive positive constant. Okay, thanks. When alpha is equal to 0, then the mother black hole is non-rotating because J becomes 0. Now we have checked that when for this non-rotating black hole, we can easily, if I put this J to be 0 in this six-peak equation we started with, the one solution definitely we find that delta J equal to 0. But also if I put this alpha equal to 0 in this f of alpha, we'll see a non-zero f of alpha. That basically means that there exists another solution, surprisingly, with a non-zero f of alpha, which suggests that there is an under-rotating RFD dual black hole that actually dual to a non-rotating black hole. And when I set alpha equal to 1, that sets both the over-rotating and under-rotating black hole to a small black hole. Hence, also the dual black hole is also a small black hole. And though there is a solution for them with a positive j plus delta j positive j hat, but still we are not interested in these two particular regimes for alpha equal to 0 and alpha equal to 1. What our main interest is when the mother black hole is over rotating, that is when alpha is more than 1, and under rotating when alpha is less than 1. And how this RFD dual black hole behave look in this case, like if I start with a over rotating mother black hole, whether the RFD dual will be also over rotating or under rotating or not. That's what we are mainly interested in to check. That we can nicely see the form of this dual black hole from this card. So in this plot, we basically plotted these two quantities. One is j hat square by s naught square, another is s naught square by s naught tilde square over s naught square. And earlier slide we mentioned that depending on whether j hat square is more than s naught tilde square or less than s naught tilde square, depending on that the black hole is over rotating or under rotating, the dual black hole. So we can say that when the alpha is less than 1, we can see here this s naught tilde is more than j hat square. That means for alpha equal less than 1, both mother black hole and the dual black hole are under rotating. And when alpha is more than 1, then this curve is dominating. So basically for alpha more than 1, then j hat square is greater than this s naught tilde square. So in this case, both the mother black hole and RFD dual black hole are over rotating. So we can see that under this our proposed rotational fundamental duality, and over rotating black holes remain over rotating, dual to over rotating black hole, and under rotating black hole is dual to under rotating black hole. And there is no such possibility under this RFD, there is no such possibility among mapping between over and under rotating black holes. Okay. Now similarly for W extremal black hole also there is some sextic equation for which we solve this delta j. How much time do I have? Okay. And like for them also we find a unique solution for delta j which keeps this j hat, that is j plus delta j positive. So here we show it numerically for a fixed values of this entropy. We can see that there are two real solution of delta j, but only among them only one keeps this j plus delta j positive. Now again how the solution looks for this case, again we said the alpha as a ratio of j square over s naught square, and here in this case we ratio between j hat square over s naught square, we set it as h of alpha, and here the h of alpha takes the following form, the following function of alpha, where omega and omega square are two non-trivial cube roots of unity. Now we can write the entropy of the W extremal black hole with a charge q hat and angular momentum j hat in the following fashion, where s naught tilde related to the s naught and h of alpha in the following way. And here we are plotting how this j hat square and s naught tilde square behave with alpha. We can say that for any positive alpha, this j hat square is always s naught tilde square. Though in this case, I mean nothing matters whether j hat square is less than or more than s naught square. And for the special case, again here also if I set alpha to be 0, from the sextic equation we find that there is obvious solution delta j is also 0, which means that one non-rotating black hole maps to another non-rotating black hole. But there is also another special solution which says that there is a non-zero values of h alpha. So basically here also in this case also this RFD dual maps one non-rotating black hole to a rotating one. So now I will summarize. So our claim is that under our proposed rotational fundamental duality, two charged extremal or double extremal rotating black holes with different angular momenta, they have the same entropy when their charges are related by rotational fundamental duality. And I'd like to mention that in this case, in this proposed case, that definitely the charges, the definition loses this anti-involutive property that loses that as compared to the trivial fundamental duality. And we have proved that this mapping is unique, and an under-rotating black hole always remains maps to under-rotating black hole under this duality, An over-rotating black hole always maps to an over-rotating black hole. Now, so far we have just considered black hole solution in this case for a two derivative theory of gravity, classical theory of gravity. For them only we check this Freudenthal like duality or some duality of some charge transformation that keeps the entropy invariant. Now, in future, we'd like to explore the possibility of having this Freudenthal like invariance for black holes, that solution of higher derivative corrected gravity or quantum corrected solutions. Okay, thank you.
Questions?
We non-extremal not yet done, but we have done. There is also works for near extremal black holes, and that's just and which near extremal black hole like it has a temperature, small temperature, and temperature that enters in the form of the entropy. So in this case, it generalized as such that two near extremal black holes with temperature for say T1 and T2 with different charges, and these charges are related by some nonlinear fashion, but they also have the same entropy.
Okay, and you also had a scalar field, right? So if you don't have the scalar field in a 3, does it still work?
So if I do not have the scalar field, is basically some pure gravity. Basically, the black hole is a Reisman-Orgel solution.
Okay.
In that case, basically, it's very trivial one. It trivializes to electromagnetic duality. So yeah, just one thing to mention: these dualities. I mean, this kind of duality which changes the electromagnetic charges, but still keeps the entropy invariant is electromagnetic duality. But that is very linear one. This is a non-linear one, but if it's a pure gravity, that basically trivializes to that linear electromagnetic duality.
Shindir.
So, is there anything in your computations that is dimension dependent? Like, can this be done for rotating BTC black holes?
I mean, originally it was done for. I mean, again, original version we are no more being the original version of the duality. Originally it was done for 4 dimension, but if I again generalize in some way that it's just some nonlinear transformation that keeps the entropy invariant, I mean, one can look for it.
Okay, so if there are no more questions, let's thank the speaker again. Now we'll break for lunch. We'll meet again after the lunch.
नीचे पता ଆଇତେ ନା ଲାଇଭ୍ ଅବିକା ଗଲା ବା ଏବେ ଗଲା ଟିକେ ବନ୍ଦ କର control L
हेलो कैसे करते हैं
ऑन हेल्प यहाँ पे म्यूट दिख रहा है इधर क्लिक करेंगे तो म्यूट आ रहा है
अभी ऑन
ये अभी ऑन
Okay. Okay, let's get going with the second half of the last day of this ISM. The next speaker is Pramod Shukla, who is going to tell us about inflating with fibers and Swiss cheese. Pramod, the floor is yours.
Hello? Yes? Am I audible? Yes, okay. So thanks a lot. So let me start by thanking the organizers for giving me the opportunity to speak here and having this wonderful conference. They have really put tremendous amount of effort. So I'm going to talk about something on inflating with fibers and Swiss cheese. So, it's like living with two words, asking the question, is this true or that true? So luckily both are true. These are philosophical questions that you have like two things to choose. So unless you see some discrepancy between the two. Okay, so we have been always occupied with finding the kind of attempts, making the attempts for connecting string theory with the real world. So let me start by thanking Ashok Da for yesterday's very interesting public talk, which got us back to the core goal, which as a string theory community we had, finding those phases, finding the Calabi-Yau. So this talk is really about finding the Calabi-Yaus. So and in this conference we had two very excellent talks by Liam and Tim, which was also connecting the string theory with the real world in the sense of doing some phenomenology. So so I'm going to talk about some strings and some Swiss cheese. So I plan to give it before lunch, but virtual cheese are not good enough when you are hungry, so it was postponed to the post lunch. So but I'm still going to give you it, and if you're not over full, then you can take it. So the idea is to kind of do some kind of attempts which takes some string model to some realistic thing, and this realistic is a very relative word, so it depends how many things you want to accommodate in a given setup. So that would be the goal, and this is based on this one paper which already appeared with George, which is who is in Ioannina in Greece, and one paper. So this 12 has started from 09, so if you don't see in 12, maybe you don't be surprised. So depending on time, because it's very hard to cook cheese with Swiss cheese with the strings. So, and I'm really not a very good cook in that sense. It's taking a lot of time. So getting back to the outline, so I will be talking about some kind of some old stories, maybe some 15 slides, maybe 10, and this would cover like what LBS is, what fiber inflation is, and some global embedding, and then we'll discuss some new story in terms of some new challenges, that have some field range bound and scale separation, which actually Tim talked about. So far we have been like very positive in our approach of constructing the realistic model, but for last few years we have been well critic and sometimes maybe over cautious and extra critic. So we would like to kind of give that kind of balancing thing between this, and we try to kind of the main goal would be try to find some Calabi-Yau which are non-Swiss as well, and do some assisted nature of fiber inflation. So with this, as I think Liam very nicely kind of described, so the low energy dynamics is covered by some building blocks, namely the scalar potential and superpotential, and then one can have n equal to 1 scalar potential which has a series of corrections coming from alpha prime and extreme loops. So the idea is once we do the string compactification, moduli are inevitable, and we have to fix those moduli in order to have some, some prediction in the theory. So there are two schemes for fixing the moduli, the KKLT and the LVS. The KKLT was very much, discussed in detail in Liam's talk, and this is the second story which I am going to tell. So the KKLT may have, so there is two issues in the beginning. KKLT finished like 22 years, LVS is finishing 20 years in this. So you can see that these schemes are there in the market for quite long. So then the main issue in KKLT was how to find the low W naught, because this determines the size of the Calabi-Yau. And this recent strategy of Liam and others, they have found that this so-called tuning requirement of W naught is a bit more natural these days due to this perturbatively flat flux vacua, what they call PFFPs. And I would be discussing this LVS, which has a different implication and different scheme. So the idea is we start with hundreds of moduli, and if we try to build the model of inflation, we have to somehow give the web masters to all these moduli in such a way that we have some hierarchy and we get a single field effective potential which is flat enough to drive the inflation. So that is the kind of rough idea for scalar models of inflation within string theory. And for that period, this flatness has to be protected for long enough time. That means we have to be having some symmetries which we could actually do it, so called this no scalar structure and axionic symmetry. And then there are some questions about as a next step how to kind of realize cosmological observables within these settings. So these are like very broad kind of things. So what LVS is a scheme of moduli stabilization which can be described by the minimal two field Kähler moduli, and the name goes Swiss cheese because it is the Calabi-Yau which is realized as a degree at 18 hypersurface in WCP 11169. And the idea is that one divisor of the Calabi-Yau contributes positively, other one contributes negatively. So this is like some exceptional Del-Pezzo divisor, and this contribution negatively is like a holes inside the cheese. That's why popularly the name is given as a Swiss cheese Calabi. So we have some corrections to K, some corrections to W. This leads to some correction in the effective scalar potential with three competing terms in such a way that when you minimize, you get exponentially large, naturally in some exponentially large web for the overall volume of the Calabi-Yau. So as you know, this volume of the Calabi-Yau can serve as some kind of expansion parameter in the whole game. That's why we want it to be large, because we have to have control over the alpha prime corrections and so on. So so sometimes if you don't like some corrections. Which negative sign? This one? Tau, yes. So it actually comes from the Kähler-Kohn condition, because these are exceptional divisors. So when you go from 2 cycle volumes to the 4 cycle volumes, this conversion from T to tau creates an extra minus sign, because these are exceptional cycles inside the color. So then we have so different level of corrections can give you different things. So at the level of tree, are the divisors? These are exceptional divisors. Yeah. It's actually blowing up singularity, not dissolving. Yeah. Yes, that's true. Yeah. Yes. This minus sign comes from the Kähler-Kohn. I'll give one explicit example to say how. So in terms of the 2 cycle volumes, it's positive, but the idea is when you convert from 2 cycle to the 4 cycle, these taus are 4 cycle volumes, then there are 2 signs. So the volume you write actually, so volume you write as a T, as volume as T cube, some intersection numbers Ti, Tj, Tk. But in this case, the correct Kähler coordinates are actually these T's, the real part of which is not the 2 cycle volume but the 4 cycle volume. So you have to convert these 2 cycles to 4 cycles, and then there are 2 possibilities, plus and minus possibilities actually. Yes. So yeah. Okay. So now we have so there is whole series of corrections: higher derivative alpha prime correction, non-perturbative superpotential contribution, string loop correction, higher derivative correction. So as we see, the time evolution of these corrections have been very uncertain. So like in 20 years we have say 6, 7, less than 10 class of corrections which we have been able to compute. So computing these corrections is very hard, but once you have it, you have very rich structure to build the models. So in that sense, this time evolution, the history actually have told us that these corrections are hard to compute. So you build your model in such a way that this is having large volume, so that even if some correction is kind of discovered after a few years, you are at least you have some sense of security that your model is still surviving, because all these subleading corrections would be suppressed by the inverse volume powers. So that's how it actually goes. So this is what I call as useful control, in the sense if something is dangerous for you, just following a diplomatic approach, because we try to take that dangerous thing on your side. So that's what LVS does actually, and assimilate things in the game. So alpha prime corrections actually it is included in LVS, so that so it becomes the part of the game, and that's how one has the LVS. So the idea is how the viability of the LVS itself is. So from time to time we have seen that it has been more robust. For example, one new correction of the string loop type was found dominating at the level of scalar potential. You see, there is domination by this side, but at the level of scalar potential, it turns out that this term is identically 0 because n equal to -2. So there is a t here, there is a t cube down. So this KGS is a homogeneous function of degree -2. And this term precisely cancels. And this is something known as extended low scale steps. So in this historical development, we have seen many a time that LVS have been proven to be more and more robust. And all these subleading corrections, whether we know it, then we know it. We find that they are suppressed by some powers of volume. So that's why volume acts like some expansion parameter in the whole game. So then there are very naive steps of taking the string inflationary model. So the idea is to start with some K and W, the ones which you like, some answers, and then try to realize whether those answers and those assumptions are really achievable in a given construction of Calabi oriented. So that's why this global embedding is important. So for example, if we have some LVS model, 2 moduli are fixed by LVS at the minimum level. So if you have 3 modulus case, 3 parameter case for the Calabi, H11 equal to 3, then there is one extra modulus which remains flat at the leading order of LVS. So that flat modulus you can engineer in such a way that you drive in place request model. So that is the whole game, and by this way, depending on the type of inflaton in the geometric sense, so we have different types of inflationary model within LVS. One is known as a blow-up inflation, in which case the inflaton is a blow-up modulus of some Delpezzo divisor. One is fiber inflation, which I would be discussing, and the other is actually the poly-instanton inflation, in which actually instanton corrections appear on top of the instanton. So there is actually the poly of it, and so depending on the geometric nature and the type of the corrections which are inducing these inflationary potential, we have different classes of these models. So why we do global model building is that we have too many models actually, and it's very hard to distinguish which one is correct. So one thing would good to have some theoretical lab in which you could kind of have some kind of preference, or at least you can rule out some model. And global embedding really does that job in the sense that when we do model building in naive way, we assume many things. We work with K and W the way we want, motivated by some some logic, but we don't come complete. So when we try to kind of fulfill those assumptions in a given construction, we find that it is very hard even by looking at all the Calabi-Yaus which we have in a given. So even the simple 2-field, 3-field models, when we try to build them, try to look at the Calabi-Yau database and try to fulfill all the requirements, we find that things are very difficult. It's not as easy as we. So global embedding in that sense kind of helps us to kind of discriminate among the models and see whatever presumption and expectations we've had, whether it is true to really realize it or not. So what is the reality? It actually gives us a reality test. So here is some kind of a table which works as a toolkit for global model building. So different Calabi-Yau data actually are related with different source of potential terms. So for example, H11 and H21 of the Calabi-Yau is determining the number of moduli, complex structure and scalar. The C3 are in terms of the Euler characteristic, determines the so-called BBHL correction, and then there are high derivative correction determined by this second Chern number. And of course, Calabi-Yau doesn't have the first Chern class, so we are would have some good or bad corrections. It would have been there, then we may expect something, and the intersection numbers and so on. So then we try to also realize what is the divisor topology, because different corrections need different type of divisor range settings in the model. For example, if you want to have the fiber inflation, so it involves some loop corrections, and there are 2 types of loop corrections which it involves. One comes with the so-called KK type, and KK type corrections appear when we have non-intersecting stacks of branes, and then the transverse distance between these stacks actually determine the failure position. And then there is winding type, in which this T actually appears, the 2 cycle volumes appear at the denominator. This is because you have the intersection of 2 D7 brane stacks in such a way that the intersection locus is a non-contractible one side, because it appears in the denominator, so it should not shrink into 0. So it should be some torus or something. So when you build explicit model, then you have to check all these assumptions which you naively make, whether they are really realizable or not. So that is the kind of stability criterion. Yes, I mean we consider the Calabi-Yau which are K3 fibers. So stability criteria in which sense, for instance? Yes. So we test it in terms of different implications. For example, stateful cancellation conditions we check that they have to be matched. and other intersection like Friedbitter anomaly. So these things we check, which can be combinatorially checked. So in that sense, we are checking some implications which. But so far we are not realizing the local model in that. There is no MSSM. I mean, that's why these two stories go. So once we consider to the gauge group with the specific bundle, then those stabilities are more into the game. But so far we are looking at the global properties of the Calabi-Yau with some information on the divisors and curves. So then this scalar cone condition actually fixes. It actually imposes some kind of restriction on the so-called flight directions once we have LVS. So we'll discuss about some detail on these. And so this is the fiber inflation model. The very minimal thing is that like you have two moduli are fixed by volume and tau s are fixed by LVS, and there are three moduli in total, tau b, tau f, and tau s. And the idea is that the third modulus is having a subleading correction coming from the string loop type, and this can be written in these three terms. So these two terms actually determine the minimum, and then there is a third term which determines the steepening because tau f is in the numerator, and one has to kind of balance some way in this A1, A2, A3 in such a way that you have long enough play to drive the inflation. So it's a very nice model of inflation which gives the tensor to scalar ratio quite non-trivial to be detectable in future. That was the attraction of this model, that it is a super Planckian model of inflation which has a stable tensor to scalar ratio. So this is the very naive way of saying it, but if you want to go the concrete model building, we have to kind of ask all these questions, whether find the Calabi-Yau, how to realize that number of loop corrections are there which are appropriate and not too many, because if you have too many loop corrections then they might spoil the whole inflationary plane. So they have to be appropriate and also enough. And then high derivative or other correction, you have to see how the models actually is robust against those known or unknown, maybe in future known corrections for the model. So here is like so although this is like belong to the hidden sector, this Calabi-Yau, but implications of this hidden sector is omnipresent in the 4D effective theory, and we have like very nice data sets. So for example, if I recall in my PhD time, we have very few Calabi-Yaus known, like so this 11226 was there for K3 fibration, and this 11169 mid 90s from Candelas and others. And then in maybe 2003, DDF, Dennis Douglas Floria came up with the more detail. So Calabi-Yau classification was there, but not at the level of divisor topology and the intersection numbers and so on. And then this pulp actually came, this package for analyzing lattice polytope, maybe 2007-8, then Sage and combined with Sage and Singular. There was a new version of pulp in 2010. So we have been like working continuously on finding the right Calabi-Yau in all these years, in last 15 years or so. And as Liam discussed, currently we have very powerful tool in terms of the Calabi-Yau tools. And this was COHOM-CAL was developed by the Munich group by Ralph Blumenhagen and collaborators. So we used it a lot. So far for smaller H11, even without Calabi-Yau tools, we are surviving with having so we have like these much Calabi-Yau geometries in the cluster Scarpe database. So now having a few Calabi-Yau in your pocket, now you are having like million Calabi-Yau in your cell phone. So wherever you are going, you are equipped with that machinery with you. And if you are a model builder, that is really very interesting. So for the case of LVS, we need del Pezzo. So it's just like blowing up some points in P2 and increasing this H11 with some constraints on the triple intersection numbers. And for having the K3 fiber, okay, so for diagonality we need. So if you put this constraint, what we find that these 4 cycle volumes, as I was saying, is related to the 2 cycle volumes. And this is in such a way, if this condition is satisfied, intersection number condition is satisfied, then we have a diagonality in the divisor. So that's why what we call the diagonal del Pezzo, because it actually makes the 4 cycle volumes as a perfect square of the combination of 2 cycle volumes. So you can take the square root in this way, and that's how this minus sign is actually dictated by the Taylor cone. So that's how you find the holes inside the cheese. So we actually classified and gave some results how to find them and how to not find them. So for some type of del Pezzo, we never find that they are diagonal, and this was a conjecture yet to be proven for general H1. So then for K3 fibration, there is a very nice theorem of Obisho, which is if and only that if a divisor appears only linearly in the intersection polynomial, then the Calabi-Yau threefold is either a K3 fibered or a T4 fibration. So very powerful, or a P1 base. So in this case, we just see that when the cubics vanish and when the all the quadratics vanish, and we find that this is only K3 and T4. That's what the theorem says. So we have to look at just the intersection polynomial and see that if a divisor only appears linearly for all these possibilities, then you have a K3 fiber. So in this case, it actually takes this kind of form, which was needed in fiber inflation, if you recall from this. So this kind of thing we need. So naively we assume that, but we have to find the right Calabi-Yau which really gives me this thing what I assume. So in that case, so we have so this is like a toroidal like volume, so volume is like just T1, T2, T3, say T6, T2 times T2 times T2, upgraded with extra del Pezzo. So we find a Calabi-Yau which is really there in the database, which actually like the toroidal upgraded toroidal version of del piezo. So we include more one more extra del piezo. So sorry for this heavy slide. So it doesn't mean to say anything. It just says that you have to find all the divisors and curves to say which corrections you are having at what time. And this number is very small. So we actually this fiber inflation model was given in 2008, and after 8 years we came up with after 8 years we came up with the right right global embedding for this. But it also has some kind of things some kind of issues which we missed at that time. So I won't go into detail of this slide because there is a similar of one for the current example. So the idea is when we fix the overall volume of the Calabi-Yau in LVS, that means we fix the volume and the del piezo volume of the overall Calabi-Yau and the del piezo. So if you have say 3 modulus H11 equal to 3, so there are 3 scalar moduli. 2 I have fixed in LVS. So one extra, I think that it is like a flat direction. So I can move it the way I want. But that is not true, because as soon as you fix the overall volume and the volume of the del piezo, the so-called the modulus which is still flat is actually bounded by these two. So this is what is known as the inflate on bound range problem in fiber inflation. That is somehow the Taylor cone condition kicks in between, and it's kind of kills your plateau. So you have less number of e-foldings. This is what we observed. So of course we can actually make the volume large and make this delta phi large enough. But what happens when you make your volume large? Your scalar perturbation amplitude is actually diluted in cosmology. So then these things are actually not compatible. So volume has to be like 1000 in fiber inflation model, and 1000 means you cannot go beyond say 3 or 4, maybe 4.5, and you kind of kill the plateau by this kind of variation. So, and this was before the swampland revival, what we observed, but we thought that maybe it is just the wrong Calabi-Yau. Maybe in some Calabi-Yau you could solve this problem. Okay, so what are the possibilities? The one possibility is to leave the Swiss cheese. It's too bad, I know, because we like this like cheese. So we have to because the del piezo is creating the problem. You see, the del piezo volume is coming not only as in the lower bound side, in the upper bound side. So somehow this del piezo, which was very nice for having this Swiss cheese like a structure, is like a villain in the game now. It is killing the plateau of inflation thing. So the question is, can we have no del piezo but you don't have LBS now? So all the nice thing which we developed is actually at stake. So question is how you find still LBS like model without having the del piezo divisor or Swiss cheese structure. So we try to find some model and do some kind of inflationary analysis by multi-field, so that multiple fields actually drive the inflation. So that the burden on one field is actually reduced. But for that purpose, you have to make sure that the two fields are behaving in a like way. Otherwise, if you assign some task for 2 people, if they are like-minded, then maybe you will think that the efficiency would increase. But if they are anti-like model, then you are even making it more delayed. So in that sense, we have to find some symmetries. That's what we did actually in this sense work. So we were doing with perturbative LBS, no del piezo, that means no non-perturbative contribution to the superpotential. But there is one contribution which appears at the log loop in the scalar potential, and just at the level of 3 level, I mean the 3 level in non-perturbative series, that means without any non-perturbative correction, 3 level in superpotential, we could have this term actually. And then the idea is that it is still kind of stabilizes the overall volume at exponentially large value for the weak coupling. So this is what we call perturbative LBS. And in this model, we find that really there is one kind of Calabi-Yau which is K3 fibered and very much like the cousin of the T6, T2 cross T2 cross T2. So all the case you see, the Taylor cone condition is now like this, very nice. There is no del piezo, so no extra bound. You can make the way you can want. And if you just see this sector, for example, so if you have T4 intersection of T4s in this T6, you have the intersection locus as T2. So all the properties of this Calabi-Yau is very much resembles with the T6. So it's a very nice template when you want to go beyond toroidal without going beyond toroidal. So this is a Calabi-Yau which looks like a T6, T2 times T2 times. So in this case, we try to kind of find all these corrections how they arise by choosing some orientifold X7 with some brain settings. I won't go into the detail, but yeah, but then we try to kind of ensure that symmetry which is already there, 1 going to 2, 3. So this kind of Z3 symmetry is already there in this model, and the scalar potential has this term uplifting. So it's needed for having de Sitter from NT de Sitter. NT de Sitter is found by this. So these are the leading order contributions in blue. Then we have the sub-leading contributions from the winding type stem loop corrections and after the 4 correction. This helps in drive the inflation. So I'll just come to a bit fast. So now because I don't have time, so I would just stop working with time variable. I'll go with the e-fold variable. Number of e-fold dn is actually s times dt. So we just get rid of time. And then we can see that this Friedman, this standard textbook thing is actually this Einstein-Friedman equation can be recast by using some useful relation in such a way that the slow roll parameters epsilon and eta are there, and then this equation becomes second order only in terms of phi's. So everything depends just on phi's, your metric, your potential, all this just depends on the fields. So no Hubble appears. So Hubble is actually just eliminated. This one is eliminated by using this useful relation. So then we actually make some kind of, these are the cosmological observables which we need to match. Cosmological observables which we need to match, and we find that, okay, recently there has been some activators, so-called this ACT plus DZ, which actually increases the value of NS a bit. So we have to kind of realize this cosmological observable in terms of epsilon and eta parameters, which are related by the derivatives of the potential to potential ratio. So we find that these blue pieces actually determine, it's like Starobinsky-like inflation. So if you could ensure that R1 and R2, which produces the steepening part in the given model, if they are very small, then we could trust this model for driving enough e-foldings. So we can see that in this case R1 and R2 are indeed volumes of this. So our large volume is actually helping us in kind of having the control over the steepening part to have long enough plateau. So this is the one field model, and we can see that a single field needs around 5.7 Planck units to have the 16 folding and all the cosmological observables. So we want to go beyond. Actually, this is just the interesting evolution how the single field actually gets into the attractor. So this is the multi-field model in which we can see that the volume is fixed by the perturbative LBS. Then T1, T2, T3 are now very like-minded fields. They are symmetrically appearing if we choose these coefficients accordingly with that symmetry. Okay, so then we can see that it's like, if we are using the canonical fields, we are like in flat space, and then the distance is just like the Pythagorean diagonal thing. So now the burden of kind of going for 5.3 field excursion in Planck units is actually shared by two fields, 3.7 and 3.7. So that's how you see. So now two fields are helping together each other to drive the same e-folding without traveling that much distance. Because traveling large distances is already creating problem that you have many states which could appear in the game. So here is just like some stability condition, because we are having many types of terms. So this shows how those terms evolve in terms of e-folding at different states. So this is de Sitter uplifting part, this is radius. So you can see then you kind of merge them. So then you can have how the potential is almost flat when the e-folds are there till it becomes into the minimum. And then scale separation, which actually Tim described in detail in his. So scale separation appears to be some problem here when we try to do. So this inequality has to be satisfied, that mkk has to be less than string mass, this gravitational mass has to be more than Hubble. So these are a bit quite strong constraints, and when we do for all the moduli, we find that either towards the Hubble exit or towards the minimum, at least one field is there which is getting towards the kk scale. So in that sense, although this model has many nice features, but it is not the ultimate model. So that's how we become cautious in our claims these days, that we want to revisit things a number of times before we really come to that thing. So in this case, the problem is there that either it is at the minimum side, it is one kk scale is getting closer to one moduli mass is getting closer to kk. That means this whole tower of states which may enter into the game, or on the Hubble exit side there is one scale which is getting closer. So all these are nicely attracted to their minimum effective behavior. So I just kind of summarize by giving the conclusion that we discuss what, why, and how about LBS, and be motivated by taking a kind of phenomenologist approach, that how different topological properties of the Calabi are actually helping us to build our model with very specific engineering which is required. And then we discuss fiber inflation and perturbative LBS, and we try to kind of add to like-minded fields to drive assisted fiber inflation. And we are working on that. We can again get back to the Swiss cheese, because Swiss cheese was really very nice and serving many other purposes. So we are trying to see whether these difficulties can still be overcome by going to some Calabi or which larger ratio. So thank you very much for your kind attention. Yes, please.
Questions? Is there a preferred value of the tilt in this model, or you can just tune it to any value you want?
No, you mean spectral tilt? So
yes,
that actually we chose because in recent month or year, this ACT and DAISY are having more attention. So we wanted to get the preference for these actually. So you see, so earlier, I mean, for all these, this Planck data was requiring 0.965, but now we need a bit larger side of the tilt, like 0.974. So although this looks very small, but it actually has the potential to kind of discriminate among many models. So, but this model is flexible enough to kind of accommodate, because we can play with the plateau in such a way that, you know, it can either go up here or down. So this actually the kind of curving of this plateau here, I mean this steepening part or the downing part, can make the NS a bit large or small the way you want. So you have to kind of make the parameters, this model dependent parameters in such a way that it does the job.
Thank you.
Maybe one more question if there is any.
So in your potential, you had some terms proportional to zeta2 and zeta3. Presumably, there are higher derivative corrections coming from 10 dimensions.
Yes,
right?
yes, yes.
Is it? I mean, can you have a parameter range such that higher derivative corrections would be further suppressed to those ones, or you would expect?
So yeah, that's why I motivated in the sense of LVS. As soon as we ensure that most of the corrections are like, you know, volume suppressed. So even if we don't know some correction in future, it has been proven that some corrections which were known later on, they are also volume suppressed. So like this hard derivative up to the 4 correction. So these corrections come beyond the, you know, so we have r power 4, then we have r square g square, r cube g square, which is at the level of 2 derivative. But we can go to 4 derivative by r square g3 power 4, like w naught power 4, this book of alphabet. So this whole series actually goes to f to the 4, f to the 6, and f to the 8.
So you have parametric control on those corrections.
Yeah. So in that sense, we have the control, because these extra corrections, the high derivative f to the 4, they appear with the 1 over volume to the power 4. So there's a t in the numerator, but t is just like, even if the largest t is just like volume to the 1/3, because it's a 2-cycle volume. So for the overall Calabi volume, it can go like maybe volume to the 1/3 for the mostly isotropic cases.
Okay, let's thank Pramod again.
Thanks. Thank you.
Next is Christian Jepsen. Christian Jepsen, who is going to tell us about uplifting string amplitudes.
Yeah. Hello, everyone, and thank you so much for the invitation. It's been a real pleasure to be part of this meeting, and I suspect many of you may be wondering, what on earth do I mean by this process of uplifting a string amplitude? So let me help you demystify the subject of this talk. But let me just start by a brief word of preface to say it's based on these 2 papers. One of them with the great collaborator Emil Bjerrenborg. So you can refer to these for more details if you wish. And so yeah, let me now try to introduce and motivate what exactly will be the subject here of this talk. So you can consider the talk part of a sort of ongoing trend within the S-matrix bootstrap, where people are sort of reviving old dual models that have been neglected for many decades and looking at them, you know, now with the benefit of all the things we've learned about scattering amplitude since then. And so what we're going to look at is a specific family of dual models due to Richard Brauer and Peter Goddard. And so the basic idea is that if you integrate over basically a circle, right, then with some conformally invariant integration measure, then you get the open string amplitude, right? And if you perform the similar integral over the sphere, then you get the closed string amplitude. So the dual model proposed by these two gentlemen is the model you get where you integrate over a hypersphere. So in some sense, it's meant to be some kind of model of higher extended objects. Okay, and let me mention too, a key aspect of our talk will be to uncover a partial amplitude decomposition. So the distinction between full and partial amplitude will take center stage during this talk. So yeah, just sort of a brief little reminder of things I'm sure we mostly know and cherish, right? So for example, in the context of QCD, right? Like when you have sort of, so this is at tree level. So when you have a full amplitude, you can perform this kind of color kinematics decomposition where you write it as a sum over permutations that don't involve the cyclic permutations. And then you basically have all the group theory sitting in front, and then you have these partial amplitudes where all the poles now, they sit only in channels that respect a given cyclic ordering. Okay? And so in context of string theory, right? Like how does this come about in string theory, this kind of decomposition? And so the idea is if we think of a string as a kind of flux tube that connects a quark and an anti-quark, right? Then basically this decomposition, it comes from a sum over the boundary insertion. So this is in the context of open string theory, right? And so then these different boundary orderings you can associate with Chan-Patton factors, right? And they can be interpreted as labels that the string can end on, right? And so this kind of prefactor we saw on the previous slide with the group theory in it, we can think of that as coming from tracing over the Chan-Patton factors. So yeah, I couldn't resist duplicating these figures from Greenford's written. So this is sort of an old story so far, right? But so the point is, since these Chan-Patton factors, right, are associated to the string endpoints, right, you wouldn't really expect that there should exist some kind of partial amplitude decomposition for extended objects beyond open strings. But so what we'll see today is actually that not just this our Goddard family of dual models, but in fact even the familiar via pure amplitude that we know, actually they do admit a kind of notion of a kind of partial amplitude decomposition. And so let me give the huge disclaimer right off the bat is that we'll be working in the context of sort of bosonic string theory. So everything here will be tachyonic. Okay. But actually, you shouldn't be too discouraged from this, because actually some of the functions we'll run into actually the kind of, there were like sort of bottom-up S-matrix investigations that kind of stumbled onto these same functions, not knowing it was that they also were these tachyonic models. So you could say a more broad questions we'll address is whether these kind of closed string or whatever objects we might think of as the Brouwer-Goddard hypersphere models represent, if there's some way to distinguish them. Because so the point is that in a full amplitude, right? If we have four identical objects that we scatter, then we expect it to be fully symmetric in the ST and U Mandelstam invariants. Okay, but if there's some way to distinguish them, then we should be able to get some 2-to-2 scattering where they aren't all four identical objects. Also in such a way that like the four scattering channels don't give completely identical poles. And so we'll see that at least on the mathematical level, this prerequisite is actually met. Okay. And then finally, a last way to view the talk is I'm going to argue that there actually exists a kind of meaningful notion of dimensional continuation, not just for the target space, but for the dimensionality of the world sheet or the world volume. So with that sort of little introduction out of the way, let's look at the precise model, right, that we're going to analyze. And so yeah, the model is from 1971. You can see it has very few citations, right? And remember, two of these citations are like from the papers I showed you at the beginning. But so their basic idea is that where normally you have this Kober-Nielsen integral you use to get string amplitudes. Now instead of integrating over a two-dimensional or one-dimensional integral, we take it a general d-dimensional integral, right? And so right here it's the hyperplane, right? But this integral, as I'll talk about on the next slide, has some conformal symmetry. So like you can map it between whether you're integrating over the hypersphere or the hyperplane. That doesn't really matter too much. Okay, and then similar to the usual string theory amplitude, you basically can fix. So we'll be looking today at a 4-point amplitude, and so in that sense there'll be a fourfold integral. Okay, but just as in string theory, we can use the symmetry to fix 3 of the integration vector variables, in this case, to any value we want, labeled with its A, B, and C. Okay? And actually, So I would argue this is sort of the most natural way to do a higher dimensional version of the Kobayashi integral. And in fact, it's so natural that it was independently discovered by this person, Makoto Natsume, who was a PhD student of Polchinski, and Polchinski had assigned him this problem of trying to come up with some like brain amplitudes. Okay, and yeah, even fewer citations, and again, 2 of them, yeah, you've seen already. So already from the integration formula, you can see that you have sort of translational and rotational invariant, right? Because the integrand depends only on the norms of vector differences. But so it turns out if you choose the special tachyonic kinematics, right, then in some sense you get some weight from the measure that cancels with the weight from the integrand, right? And the upshot is that actually this whole integral becomes invariant under dilatations and special conformal transformations. So you get the full conformal symmetry, and that's why on the previous slide, you know, we were able to have these 3 vectors we could fix freely. And let me mention, in some of his later papers, Siegel had some comments about about some preliminary discussion of supersymmetric versions of this, which you know, we will not be talking about today. Is entirely bosonic. And so the integral I showed you, technically it's divergent, but there's several ways you can regulate it, and you obtain this answer, which was also obtained by both the 2 papers I cited on the previous slide. Okay, so if you set d equals to 2, you get the Via-Shapiro closed string amplitude. And if you set d equal to 1, then you get the Veneziano amplitude, except with a caveat, right? Oftentimes when people say the Veneziano amplitude, they're talking about the beta function. So this here is the full amplitude, so what you get from summing over the 3 beta functions depending on ST, SU, and TU. Okay? And from the poles of these gamma functions, you can see that the S-channel poles are situated at a value. It starts at -d, and then it jumps by steps of 2. So yeah, as I mentioned on the previous slide, I've solved alpha prime into the Mandelstam invariant, right? So I'm working with sort of dimensionless momenta. Okay. So yeah, again, related to the caveat I gave you earlier, like the larger you take d to be, the more tachyons you get. You're basically shifting the whole string theory spectrum into an increasingly tachyonic regime, right? So that's sort of the main price you have to pay to look at these models, okay? But at least a positive thing is that you'll notice that you can check. It's not too hard to check that if you look at the t-dependent residue on an S pole, then it's going to be a polynomial and vice versa, right? So that's what locality requires. Okay, what about unitarity, right? So since we're working at tree level, unitarity just gives you an inequality. So what you can do is you can look at like the first many residues and decompose them into partial waves and see if the coefficients are non-negative as required by unitarity. And basically, if you play this game in the case, so just for the open string amplitude, you sort of obtain a bound that exactly contains the critical dimension. And if you try to play the same game so now notice, right, there's a capital D. Capital D is the target space dimensions, right? So we have little d, which is the sort of uplift, the dimension for this Kobayashi-like integral, and then we have capital D, which is space-time. So the point is then, basically for the closed string amplitude, the sort of bound you get just from the 4-point tree level amplitude are actually even bigger than the critical dimension, right? Like it's only a necessary condition. It's not a sufficient condition. And then you can check, yeah, that this bound, it's some value bigger than d as for these values of the hypersphere dimensionality. And then once you reach 6th dimension, then you're back again and exactly at a bound of 26. And then curiously, if you consider this sort of weird limit where you take the hypersphere integral to be of like infinite dimensionality, and that limit, this sort of bound on the target space dimensionality actually asymptotes to 10. Okay, but so now we'll sort of turn to the main theme, which will be a kind of partial amplitude. Okay, and so to sort of set a stage, right? Like let's just remember. So the point is that, you know, as I talked about for the Veneziano amplitude, right? The sort of ratio of gamma functions I showed you comes about as a sum of 3 beta functions. And so the crucial point here is that the partial amplitudes, right, they are themselves in some sense physical, right? They satisfy positivity, they have nice high energy limits. And the fact that they each individual are sort of healthy physical objects is what means that you can put coefficients in front and have something that's still physical. Like in some sense, that's what enables you to dress them in Chan-Patton factors, because it doesn't rely on any delicate cancellations between these different terms. Okay. So now, the way that, like, at least one sort of very natural seeming way to obtain this decomposition is you look at the integral over the circle, right? You have, or over the line, depending on your preference, right? You have 3 points that you can fix to whatever values you want, right? And those 3 points that you fix, they naturally split the whole region into 3. And so carrying out those 3 separate regions gives you each of the 3 partial amplitudes, okay? But like, how then on earth would you do this for higher dimensions? And so as the natural starting point, we'll just ask sort of a kind of neutral question. We'll just ask, what's the largest number of terms into which you can split this sort of general Brouwer-Goddard model, right? Like any function, of course, is equal to itself. So the answer is at least one, and then potentially there might be multiple distinct terms related just by shift of the argument you could write it as. It turns out the largest number you can get is 6. Okay, this is like if you just want the maximal mathematical decomposition, right? And to get this kind of decomposition, you're actually breaking crossing symmetry, right? Because otherwise you can't have a distinct ST and TS term, for example. Okay, but then the question is, are these building blocks actually physical on their own, or are they not, right? And you probably won't be surprised to hear they won't be physical, these building blocks. Yes? Yeah, so maybe I can show how to derive it concretely. But in some sense, you can argue just from the fact that you have 3 Mandelstam invariants and 2 of them are independent, that 6 terms is the maximal number. And then you can explicitly derive such 6 terms to know that that's a decomposition. So far it's just mathematical, like a mathematical fact. But at least maybe the way the decomposition comes about does contain some physics, because sort of a way you can carve out, like a way to obtain the decomposition is by partitioning the integration domain. And you can do that, you want to do this in a way that respects the conformal symmetry of the integral, right? And so a way you can do this is by using the conformal cross ratios. And so at 4 points, you have 6 conformal cross ratios, right? I mean, 2 are independent, but you have 6 numerically distinct. So that means that if you use those to carve out, you can use those to carve out your integration domain according to which of these 6 is larger than the others, okay? And so if you integrate over one such subdomain, then you get a building block that will lead to precisely the decomposition I showed you on the previous slide of 6 terms just related by shifts of the arguments, right? Because basically, you know, these regions are all related by permuting indices, which amounts to permuting the Mandelstam invariants, okay? And so if you can actually carry out these integrals and study them analytically, and you find, no, they're not physical. Particularly what they violate is they have very nasty high energy theory behavior, right? So you can imagine building up later on loop amplitudes, right? They would give you nasty divergences. So to cancel this kind of unhealthy UV behavior, you have to add them together pairwise, okay? And so in this sense, we've kind of arrived now at having 3 building blocks, like this sort of decomposition into 3 partial amplitudes that we have in the usual string theory case. So in some sense, this is like sort of as close in this context as we could get to like a kind of derivation of crossing symmetry. And then we know that in the case when D is 1, this just amounts to splitting the beta function into into a sum over 2 2f1 hypergeometric functions. So it's not sophisticated at all mathematically, right? Like, you know, as we've learned from Sinha's talk, right? Like, you know, there have recently been discovered much more general ways to decompose the open string amplitude. So what this discussion leads us to conclude is that we ought to define sort of the way we can define a partial amplitude is by a combination of such 2 domains here, by 2 of these kind of domains we defined earlier in terms of conformal cross ratios, and then associate a partial wave to each domain, and then this way we automatically get something that sums up to the full amplitude. Okay, and to see this more concretely, we can let's perform like the standard gauge fixing choice. We said 1 vector to 0, 1 to the unit vector, and 1 to infinity. Okay, and so in this case, you can see that the 3 domains you have are mapped to each other by a combination of a translation and a special conformal transformation. In the special case where you use the unit vector for both the parameters of the transformations. Okay, so this is the combined transformation. So the idea is here you see like this is how the total integration domain is sort of carved out into 3 colors, right? And then there's an extra rotational symmetry about the x1 axis. So the point is, if you perform this transformation I showed you on the previous slide, each region gets mapped to another region. But in mapping the regions to each other, you're permuting the 3 sort of gauge fixed values, right? Which you can cancel by changing the indices, which amounts to like changing the momenta argument. So this way, this kind of transformation relates the 3 arguments. So this is just another way to see that you get the same result. Like each of these 3 regions you integrate over will produce the same function, just shifted arguments. Okay? And so if you carry out this angular, I mentioned some rotational symmetry, right? So if you carry out this angular integration, basically you arrive at this as sort of the integration master formula for these kind of notion of generalized partial amplitudes. Okay? And so this was my comment about like the dependency on D, because in principle D could be complex for that matter, just at the level of this integral. But if you actually try to carry it out, it depends quite crucially on whether D is an even or an odd number. And in particular, it's much easier to carry out when D is odd. And in that case, we're able to find a closed form answers. So when D is 1, this is just the familiar, Veneziano partial amplitude, okay? And then in case when D is 3, 5, 7, I've shown you the first couple of examples, you get something built. It's sort of a combination of gamma functions and some rational functions or rational dressing factors built out of Mandelstam invariants. Okay, so it's kind of like large complicated functions, but kind of built out of simple building blocks. So they're sort of complicated in an easy manner. And you can write down the closed form answer. So the general answer is you have a meromorphic piece that contains gamma factors and some simple dressing factors. And then you have a rational piece, right? That's just fully rational in Mandelstam invariants. So that's the general structure, okay? And now, separately, if you look at these terms separately, they do contain some non-polynomial, non-physical residues, but those will cancel between the rational and the meromorphic piece. Okay, so for example, here you get this kind of polynomial with a t in the denominator when s is minus 4, but those poles cancel precisely between these two terms. Okay, and so now, if you look at the poles of the full amplitude, right, I wrote those down in the earlier slide. Starting at minus d, they go in double integer increments, okay? And now if you look at the partial amplitude, now instead you get extra poles, okay? And in the case of the familiar string theory, there's a simple explanation. So the point is, if you write the Mandelstam invariants in terms of the scattering angle in the center of mass frame, they are identical except there's a sign flip in front of the cosine theta. So that means that anything that's symmetric in T and U only contains even powers of cosines, okay? Which means that those poles will only contain even spin partial waves. So it's another way of saying if you scatter identical scalar particles, parity prevents you from exchanging odd spin. Okay? But once the particles become distinguishable, right, then this sort of no-go no longer applies, and you can sort of see the whole spectrum. Okay? So we're seeing something similar happen here for these Brouwer-Goddard partial amplitudes. So, but now getting additional poles means you have additional positivity conditions. Okay? But you can check, you can explicitly check, at least for like the first many cases, you can check that indeed they are satisfied. Okay? So now, so since we have this kind of strong analytic control in the odd B case, right? We can ask, oh, what about these kind of familiar amplitude relations, like monodromy relations and KLT relations? And the short answer is they do exist, at least on a mathematical level. You can just explicitly verify that there exist some variations of these identities. So in the case of monodromy, right? Monodromy is a relation that relates the partial amplitudes in different channels. Such a relation similarly exists, except it's at least in the simplest form to write it down, it exists at the level just of the meromorphic piece. So if you wanted to write it in terms of the more physical partial amplitude, you'd have to subtract out by hand the rational pieces, right? And so a similar comment will apply to the formula I'll show you on the next slide, which is more like a kind of KLT-like formula. Okay? So the KLT formula, right, the usual one relates the product of two open string partial amplitude to a full closed string amplitude. So sort of the more general relation we get in this context is that the product of two of the meromorphic pieces for some value d, which again, this is an odd d, gives you the twice d, the full amplitude. Okay, and you could even write down a slightly more general one where it's the product of two d's in different dimensions giving you the product and the full amplitude. Right, where again, it's an identity at the level of the meromorphic pieces. Okay, so that's it for odd d. Now let's turn to even d, including also the Villers-Sauger pure amplitude. And so the short answer is the integrals get a lot harder to do, so we don't have a strong analytic control, but what we have been able to do is define the explicit forms for the residues. And you'll notice, so if you look at the even residues, these are just the closed string residues, so they're fairly simple, right? They always give you squares, which you can also see from KLT. Now we have these additional uglier intermediate poles. And so actually you can write down a closed form expression for all the poles in terms of a 3f2 regularized hypergeometric function. Regularized just means it's stressed with some gamma functions. But this kind of hypergeometric function, it truncates. Okay, so again, all the poles still are polynomial as you would expect, and you can check positivity. Okay, and in principle, you could even sum over all the residues, and now you get a sum formula for the partial amplitude. Okay, it doesn't converge everywhere, but it actually is enough that you can compute the partial amplitude numerically for any Mandelstam invariant, either by choosing the right channel or by subtracting partial amplitudes from the full amplitude. Okay, and then again, there are other ways you can decompose the closed string, the Villers-Sauger pure amplitude, as we've learned either from their papers or from the talk. Okay, and then what about even dimensions greater than 2? Well, the integration formula I gave you earlier, you can do some changes of variables and manipulate it into this form. And basically, because of this relation, you see the way that the dimension and the Mandelstam invariant enters, you can sort of cancel a shift in D by a shift in the Mandelstam invariance, and pretty straightforwardly derive a recursion relations, that relates the partial amplitudes across double steps in D. So even D related to each other and the odd D related to each other. Okay, so either using the recursion formula or just by directly studying the poles, you can get a kind of like master sum formula that works actually both for even and odd D partial amplitudes, right? So in the odd D case, it reduces to the functions I gave you earlier. Okay, and otherwise you just have this kind of infinite sum formula. Okay, so now that we have like our ultimate formula, we can now ask the questions: are they of physical interest? Okay, and so. So they do have several properties, I think, which do make them somewhat appealing. But so the first two of these just follow from construction. Okay, so they sum to the full amplitude. That follows because we got them by carving out the integration domain. And then they have crossing symmetry, which at the level of the sum formula, it might look very non-trivial that you have a sum over. If I go back here, right, you have a sum over S poles that depend on T, which is such that precisely the same sum over T poles depending on S, right, matches it. But from the fact that we had crossing symmetry, it follows directly, right? So this was kind of an input. But now there's several properties which we did not input, which just follow from carrying out the integral. Right? So one is meromorphicity, right? If you continue the amplitude in S and T to the entire complex plane, you just have isolated poles. Moreover, these extra isolated poles are sitting precisely in between the sort of tower you had of states, right? And the extra polynomials, you get polynomial residues from the extra poles. And they satisfy positivity, at least for the many checks we've done. Okay, and then you have benign high energy behavior. The amplitude doesn't blow up nastily at infinity. And then finally, one property I think is worth commenting on, which is one I don't see discussed very often. And so I sort of tentatively I refer to it as level spin parity. So the idea is that the partial waves alternate between only having even and only having odd partial waves. So you look at the residues, you'll see that you have only odd or only even powers of cosine, which translate into the same kind of partial waves. And what's nice about this is that this would typically follow if you perform some quantization in terms of some racing operator that carries spin and mass. And it's satisfied by the string amplitudes I know of, like Veneziano via Shapiro, but also the superstring, and it's satisfied by almost none of the like Veneziano deformations that have appeared in the literature. And so now, before I close, let me just try to respond one possible question you might have, because how does this tally with like uniqueness results on the Veneziano amplitude that exist in the literature? Okay, and so here's one example of a paper from 2017, right, where they show that the asymptotic uniqueness of the Veneziano amplitude once you have like spins greater than 2. How does this reconcile? So the trick is that it's asymptotic uniqueness, right? So you can actually check that these kind of functions we've been looking at do have the same asymptotic properties. Okay. Then another one, this is sort of more recently from this year's and the previous years, where they talk about strings from almost nothing, right? From a small set of starting assumptions, they arrive uniquely at Veneziano and via Shapiro. But actually, one of their starting assumptions is this ultra softness conditions, that the amplitudes decay faster than polynomial, right? So this is not quite, a fundamental assumption at the level of unitarity and causality, locality, right? And that's violated because you remember we had this decomposition into rational and meromorphic pieces. So the meromorphic piece satisfied it, but in higher D you also have the rational piece, which just decays polynomially. I think the safest one to say is you can do I think you can do either, and you can work them out, right? Either keeping them one fixed, the other large, or both fixed and both large and fixed scattering angle. Yeah, you can work them out. But in particular, it always decays in the fixed scattering angle when they're large. Exactly. And then so my closing comment is that you might think that this is tachyonic, so what's the whole point, right? But actually what happens is often that these S-matrix bootstrap investigations, right, they tend to be agnostic about overall shift in the mass level. So what actually happened is that there were cases, there's one case I know of where they actually stumbled into one of these functions up to a shift in mass. So this is this paper from 2023 where Grant Bremen and Clifford Chung introduced a hypergeometric deformation. So actually for this specific value of the deformation parameter, it reduces the hypergeometric function that they wrote here with some gammas, reduces to these two terms, which you'll recognize is this kind of d equal to 3 partial amplitude we had earlier. Okay? And so with that, yeah, let me thank you, and I'll just leave you with this, yeah.
Questions for Christian?
I had one question related to the KLT relation. Now, the KLT relation relates the one loop open string amplitude to the tree level closed string amplitude, right?
Oh, well, I'm just showing tree level amplitudes. Like I have nothing on loop levels at this level with higher D. So right now I'm just talking about relations between tree levels. Because KLT also extends, yeah. KLT is more general, yes, but or maybe I should say there's BCJ, there's like all sorts of refinements of it, right? But like, yeah, I only have results on everything I have to say here is tree level.
So you simply take the product of two open string and you get the closed string instead.
Yeah, you have to address them with some sign factors, but otherwise, yes.
Thank you.
Hi, thanks for the nice talk. So normally when we divide things into partial amplitudes, one of the nice things about the partial amplitudes is that they're gauge invariant. So like in Yang-Mills, if you don't do this division correctly, then you're not going to get gauge invariant objects. I know that here you don't have any polarizations floating around, but do you have a sense when you do generalize this higher point or higher spin or something like this, what would happen to that?
Yeah, no, I mean, it doesn't, because it seems indeed that with this kind of color kinematics splitting, right? It seems that like the group theory prefactors live their own lives totally, right? So sometimes it seems like you could just carry out standard group theory prefactors. Yeah, so it's unclear. Yeah. So it seems to me you're not learning anything about the group theory from these kinematic integrals. I think that's the conclusion I have.
Sorry. So then, do you expect that these integrals will lead to things that are gauge invariant? I'm not sure exactly here what gauge invariant means, but like.
I mean, I think it's a bit hopeful. I mean, I think maybe that would be the best case scenario is you come up with some like generalized GSO projection that cures the tachyons and then it's meaningful. I mean, that's one hope, but then the other thing is that this is like a caveat that when you do bootstrap studies, right, like these are the kind of functions you need to find some conditions to get rid of or be aware. So I think those are the two possible scenarios. Of course, ideal case, it would point to some new physical theories. But yeah, I think to know that, you'd have to first verify like higher point positivity and so forth.
Can I ask another? Unless that's
Go ahead.
Sorry, one sec.
So you think while Boris asks.
So could you consider variants of these models where you integrate over a higher dimensional projective space rather than high dimensional hyperspheres and have some holomorphic integrals like for closed strings?
Yeah. I mean, I think it's very possible. I mean, we haven't evaluated them at all. Even these integrals were quite tricky.
But they haven't appeared in the early dual model.
No, I haven't seen them. No, but it's possible. You know, these are very few citations, or maybe there's buried some paper with like 3 citations that actually did it.
You have the question?
Yeah. Sorry.
Okay, go ahead.
So you talked about the benign high energy growth of the individual partial like the S to the S type growth. Is that right? The high energy growth and the ST large limit.
Well, I think yeah. So they well, maybe I should ask you a question.
So yeah, okay. The question I was going to ask is that in the usual Veneziano amplitude, if you choose the following limit where you take S to infinity and T to minus infinity at the same rate, you get a lower growth.
So
so I was just wondering if that.
From that limit it decays. Yeah, that's right. So that's what I would call like the fixed scattering angle high energy limit. So in that case it decays. Yeah. So it grows in one region, which is like the unphysical one, where you take 2 Mandelstam invariants to be positive, right? Which you can for physical kinematics.
Thanks.
Okay. So you mentioned about the relation to the hypergeometric representation of this Grand Riemann and Klipschung, right? So
like if I understood correctly, they started with like say 5-point amplitude and took a particular momentum configuration to get 4-point. On the other hand, here you are doing say 3 world volume, like integration over 3.
Yes.
So how do you reconcile to this two of these things?
Well, I'm tempted to say that it's almost like a mathematical coincidence, because the I equals to 1 is the only case that overlaps with one of these functions. And moreover, the rest for higher D, none of them will match. Like there's like an explicit way to see that like none of these other functions sit in the function space they explore. And you know, they also have some other papers where they introduce like a W deformation. They introduce like various directions of deformations. And this is the only point, like a single point of overlap. So I think it's just a mathematical coincidence.
Okay, thank you. Let's thank Christian again. So next up is Yunwo Lee, and he's going to tell us about fortuitous cohomologies at finite coupling. Whenever you're ready, Yunwo.
Yeah, thank you. So yeah, first of all, I'd like to thank the organizers for organizing this wonderful conference and giving me the opportunity to speak. So today I'm going to talk about my recent work, fortuitous cohomologies at finite coupling. I will explain about fortuitous cohomologies in this talk. So this talk is based on my recent 2 papers, one written with TIFR people, including Abhijit, Rajat, and Shwansh, and the other one was written with Jaehyuk, who is a postdoc at Korea Institute for Advanced Studies. And this paper written by Chang and Lin is closely related. So let me start. So one of our broad goals is to understand quantum aspects of black holes in ADS from the CFT perspective. However, there is a challenge that usually the field theory regime due to semi-classical gravity has large tooth coupling so that it's strongly coupled. So this limits direct analytic control. So we often think about supersymmetric field theory, supersymmetric conformal field theory, because supersymmetry provides access to certain protected quantities that remain well defined even at strong coupling. So one of the protected quantities that is well known is this superconformal index, and the superconformal index in n equals to 4 Yang-Mills has been shown to reproduce this Bekenstein-Hawking entropy of supersymmetric black holes in ADS5 space. The natural next stop is actually to go beyond. So this superconformal index can be computed at the free theory, so that even this and this is, since this is a protected quantity, so that we can trust this index at computed at the free theory even at the strongly coupled regime. And our next step is to go beyond just counting, but what we want to do is to construct BPS microstates explicitly and to study their spectral structure and interesting quantum properties and so on. Okay. So our playground is n equals to 4 Yang-Mills, which is the best field theory in the world according to Shiraz, and I agree. And I think all of you are familiar with n equals to 4 Yang-Mills, but let me briefly explain to you what about this theory. So this n equals to 4 Yang-Mills in 4D is dual to type 2B string theory in ADS5 times S5. And this theory has superconformal symmetry, which is PSU 2,2/4. And this contains, this group contains bosonic subgroup as SO4,2 times SU4 R symmetry, which is also the isometry of ADS5 times S5. So this isometric group has 6 Cartan generators. One is energy, and 2 angular momenta in ADS5 direction, and 3 R charges, which are 3 Cartans in SO6 or SO4 group. And also this superconformal symmetry contains 16 Poincare supercharge Q and 16 conformal supercharges S. And in radially quantized theory, this S is Hermitian conjugate to this Poincare supercharge Q. And we'll be interested in BPS vector, which preserves 1/16 of this 32 supercharge, because it is known that so if we have more supercharges than if we have more supersymmetries than this, then there has been no known black hole solutions in anti-de Sitter space, anti-de Sitter phi space. So that's why we consider this least supersymmetry conserving factor. And without losing generality, we can choose one of 16 Poincare supercharges Q as this one, and a QQ dagger anticommutator is written as energy minus the other 5 Cartons. So this 1/16 BPS states will satisfy this BPS bound such that energy equals to sum of J1 plus sum of J1 J2 and sum of R charges. And since this BPS states is annihilated by QQ dagger, you can think of this BPS state as a Q harmonic form. So what I mean here, what I mean by harmonic form is the following. So here Q is nilpotent such that it squares to 0. So you can think of this Q as an exterior derivative. So if you think of this Q as an exterior derivative, then QQ dagger plus Q dagger Q can be thought of as a Laplace operator. So a state that is annihilated by this Laplace operator is called harmonic form. So yeah, so that's why BPS states can be thought of as a Q harmonic form. Okay. So how do we find and how do you identify these Q harmonic states? So in order to identify these Q harmonic states, we have to find the states that satisfy this BPS bound, where energy equals to J1 plus J2 plus R charges. So these R charges and angular momenta are quantized, but energy is in general not quantized, and it has anomalous dimensions. Directly computing these anomalous dimensions and strong coupling is generally very difficult. So what we do is we change the problem a little bit. So instead of finding this Q harmonic form, which is annihilated by QQ dagger plus Q dagger Q, we reformulate the problem because such that we instead find a Q cohomology class. It is known that Q harmonic form, which is BPS states, are in one-to-one correspondence with Q cohomology states, which is Q closed but non-Q exact. The reason why we reformulate this problem into finding this Q cohomology classes is the following. So there has been a conjecture called non-renormalization conjecture, conjectured by these people, stating that in n equals to 4 Young-Mills, BPS spectrum at strong coupling is isomorphic to BPS spectrum at tree level. So this is a very non-trivial statement, because usually the spectrum at tree level at weakly coupling is not the same as a spectrum at strong coupling. So the argument goes as follows. So let's assume that there is a so first, this relies on the following assumption. which is that there exists a supersymmetric regularization scheme that does not change the action on Q as coupling changes. So if this assumption is true, then this supercharge Q is just Q0, which is the classical supercharge, and we know very well about the action of this classical supercharge on fields in n equals to 4 Young Mills. So yeah, so like if Q is undeformed, then we can use this Q, this classical Q, to find this Q cohomology. So the problem becomes much simpler. We don't have to think about Q dagger. We just have to think about this classical supercharge, and then just finding states that is Q closed but non Q exact. However, this argument has some caveats. So this argument is based on some perturbative arguments. So there might be a non-perturbative effects that can change this Q at strong coupling, and also there is even if the action on Q is unchanged, but there is a possible failure of Leibniz rule on a composite operator such that Q on AB cannot be this, but there can be additional contribution due to some quantum anomaly or short distance singularity. This point I will come later. Okay, so now the problem of finding this BPS states become much simplified and well defined because we know this classical supercharge expression explicitly. So the remaining task is to determine the Q cohomology. But there are many Q cohomologies. So the key question is in which cohomology classes correspond to black hole microstates. And it is useful to distinguish two classes of Q cohomologies. One is called monotonous cohomologies, and the other one is called fortuitous cohomologies. So in order to define these two cohomologies, we have to consider a sequence of gauge groups. Since we are interested in SU n and n equals to 4 Young-Mills, we consider this sequence, SU2, SU3, and this integer gauge group. And monotonous states are defined such that this state or operator remains Q closed for all n. So so this means that if you have some operator written as products of single trace operators such that it's multi-trace operators, each single trace has to be BPS. Because if a single trace is non-BPS, then as n changes, this is generically non-BPS. So this monotonous state, you can think of it as a product of single trace BPS operators, and at large n, each single trace BPS operator is dual to graviton, single particle graviton. So this monotonous states is dual to multi-graviton states at large n. And fortuitous states are defined such that which is not monotonous. So fortuitous states is Q closed only due to trace relations at special n. So if you have some operator On, which is Q closed for some specific SUN, this Q closeness is not guaranteed for other n. So yeah, this is the definition of monotonous and fortuitous states. And let me give you the simplest example of fortuitous cohomologies in n equals to 4 Young-Mills. This n equals to 4 Young-Mills has 3 chiral multiplets and 1 vector multiplet. And in these 3 chiral multiplets, there are 3 complex scalars, x, y, z, and 3 chiral fermions, psi1, psi2, psi3. And the action of the classical supercharge Q on these fields is written as follows. So Q psi1 is YZ commutator, Q Q psi 2 is ZX commutator, Q psi 3 is XY commutator, etc. And this YZ, each fields are in adjoint representation. And let us consider the following operator O, which is a triple trace operator. And as we act Q on this operator, you can see that this first trace and second trace is Q closed, because if we act Q on psi 1, it becomes YZ commutator, and Q on psi 2, it becomes ZX commutator. So this vanishes, cancels. So this is Q closed, and similarly, this is also Q closed. But the third one is non-Q closed in general. So if we act Q on this trace psi 3, psi 1 commutator, this is in generic non-zero. However, if we use SU2 trace identity, which is this, then one can easily show that this QO is 0. But however, if we go to SU3 or higher gauge group, then this operator O is non-Q closed. So that, yeah, this is fortuitously Q closed. Right. So far so good. But we wanted to examine whether these fortuitous cohomologies are really robust as the coupling changes. So we are actually relying on this non-renormalization conjecture that the BPS spectrum at strong coupling is isomorphic to BPS spectrum at tree level. So we wanted to re-examine this conjecture, whether this is true or not. And this in n equals to 4, it has S-duality property, and this S-duality offers us a good testing ground, since this S-duality relates strongly coupled field theory to a weakly coupled field theory, and vice versa. So if this non-renormalization conjecture were true, then classical cohomologies or cohomologies at weak coupling in each theory should match. So in order to test this, we studied SO7 and SP3 gauge group. Note that SO3, SP1, and SO5, SP2 has exactly the same algebra, so that they have the same cohomology spectra. So this is the non-trivial first non-trivial example. And quite surprisingly, it was recently discovered that there are actually 2 more classical Q cohomologies in SO7 gauge group than that is SP3 gauge group at some specific charge sector. So it turns out that one is fermionic fortuitous cohomology and the other one is bosonic monotonous cohomology. So this, if S-duality is true, this example shows that actually this non-renormalization conjecture is false, at least for this SON and SP theories. And since we don't think that this S-duality is false, it should be such that these 2 cohomologies should make a pair to be lifted at finite coupling. So what is the mechanism that lifts the 2? So before we said that there are some caveats in this non-renormalization conjecture, because this argument was based on non-perturbative argument, and also this. So we wanted to know what the mechanism that lifts these 2 cohomologies. Okay. So let us take a. So in order to explain what this mechanism is, let us take the regression. So which is ABJ anomaly. So I think all of you know this well, but let me explain briefly. So suppose a massless Dirac fermion is coupled to an electric magnetic field. where the Lagrangian is written like this. And this classical Lagrangian has a chiral symmetry under which rotates psi as this. And it is well known that this associated axial current J5 mu has an anomalous divergence from the triangular diagram. And I'd like to emphasize that this anomaly can play an essential role in this ABJ anomaly can play an essential role in capturing physical effects, even when the classical chiral symmetry is explicitly broken. This example is very well known. It's taught in some graduate or undergrad course, quantum field theory course. So in QCD and pion effective field theory, the ABJ anomaly controls process of decay. So so even when pions has a mass term, so that the chiral symmetry is explicitly broken, the axial identity reads like this or this. So you can see that this is still there, even the classical chiral symmetry is broken. So in supersymmetric theory, we have supersymmetrized version of this ABJ anomaly, which is called Konishi anomaly. So let us consider a 4D n equals to 1 gauge theory with a chiral superfield phi and without superpotential. Then the Lagrangian is written like this. And one can easily check that there exists a classical global symmetry which rotates a phi by some angle and keep theta fixed. So this is different from R symmetry because R symmetry rotates this theta. And you can check that this rotating this global symmetry rotates chiral fermion psi. So this contains actually this ABJ rotation. And the quantum mechanically from the same mechanism, this symmetry is anomalous, where the equation is written like this. So if there were no anomaly, then this would have been 0. But now, since there is anomaly, this is non-zero. So, and you can find that if you expand this expression by expanding the superfields, you can easily find that actually this contains ABJ anomaly equation. And also this contains the following, this contains ABJ anomaly equation because, you know, if you see theta bar, then this will contain psi bar psi with d mu, and this will have f at theta bar, so that d mu j5 mu will be proportional to g squared trace ff. So this expression indeed contains this ABJ anomaly. And when a superpotential is present, which is non-zero, then the Konishi relation generalizes to this. So if there were no anomaly, then the left-hand side should have been this. But since there is anomaly, we have this further correction. So right. So this equation has this part. So in components, this implies a quantum correction to the action of supercharged on composite operators, which is schematically written as the following. So Q1 trace phi bar psi is something plus anomalous term. And one can also derive this equation from some point splitting argument, which is that if you have a phi bar psi at the same point, you can regularize such that it can be written as this, where since this has to be a gauge invariant, if you point split, you should insert a Wilson loop in between these. And yeah, and then if you ask Q and then set epsilon into 0, then you will obtain this equation as well. So this comes from short distance singularity, as anomaly should be. So right, we are almost there. So in n equals to 4 Byung-Mills, it has been often assumed that the Konishi anomaly is irrelevant for this BPS spectrum, since the superpotential W explicitly breaks the classical Konishi symmetry. However, as we have seen in the previous discussion, this anomaly-induced effect persists even when the corresponding classical symmetry is broken. So we have incorporated this anomaly-induced correction to the action of Q, and we found that this anomaly-induced Q on this fortuitous cohomology is the monotonous one. So this means that OM is Q exact and OF is non-Q closed. So they are now lifted from Q cohomology. They are not anymore cohomology if we include this anomaly effect. Therefore, as a consequence, the classical cohomology represented by OF and OM are lifted at finite coupling. No, it's not possible. I mean, you mean like plus something such that this becomes 0. No, it's not possible. That we have argument, but yeah. So we have, yeah. So let us give a brief summary and outlook. N equals to 4 Byung-Mills provides a control setting to study Q cohomology and the microstructure of ADS black holes. And we have seen that this S-duality offers a sharp test of the non-renormalization conjecture, so that the conjecture where this we saw that this conjecture does not hold in full generality, which is because of this Konishi anomaly. So one might ask why we then study this classical cohomologies if some of them can be lifted. So the part of the answers is that so only subset of classical cohomologies are lifted, and some others remain robust and exhibit non-trivial structure. For example, I gave you the SU2 cohomology in the middle of the talk, and we have arguments why this is that this is not lifted. So even if we include all the non-perturbative and anomaly-induced anomaly effects, one can show that this SU2 cohomology is not lifted. So it's I think it's still useful to study this fortuitous cohomology, and we have shown that this conjecture is false for this SON SP theory. So a natural next step is to examine whether SUN theories satisfy the non-renormalization conjecture, and to identify precisely which cohomology classes survive quantum corrections. So yeah, thank you.
Questions for Yunwoo?
You have all the operators that you know will fail to be Q closed when you include the quantum corrections, or it is just some.
Just we have found one counterexample. Yeah.
And when you say that it cannot be corrected, you cannot add something to make it again Q closed. Is that proof, or it is just
That's
There's
true.
no obvious candidate.
So we have specific form of OF and OM, and we know all the charges. So we can just do brute force computation to show that whatever we add, like there cannot be Q-close.
Thanks.
Any other question? If not,
Hi, Anu. So, is there a reason why fortuitous and a monotonous cohomology are combined and lifted? Is this a common phenomenon, or is this specific to this example?
We don't know. Maybe fortuitous can combine, or monotonous can combine.
Has this been studied for the next level, like next not SO7 but the next non-trivial?
No, I don't have any of these now.
okay, let's thank Yunwo again. So we'll have one more talk before the tea break. So next up we have Shemanti Datta, who is going to tell us about SO1D+1 symmetry in the exact RG equation.
Hello. Okay, I would like to thank the organizers for organizing this nice conference, and also giving me opportunity to present my work. So my topic is SO1D+1 symmetry in exact RG equation. It's like I'll talk about ADS-CFT, good old ADS-CFT, but it's a different way of looking at it. So this is a work which should appear in few days with my PhD supervisor but now collaborator Bala Satyapalan. Okay, so I'll just start with SO1D+1 algebra, which is Euclidean ADS D+1 isometric group and D-dimensional conformal group are isomorphic. This is the group transformation law. The conformal transformation in D-dimensional boundary is given by this following symmetry laws. But in ADS D+1, obviously because it is in one more dimension, it have the same as whatever it is in boundary, but there is some scale dependent, some radial dependence part. So these are in Poincare coordinate, and Z is the Poincare coordinate here. So our goal is how to understand this radial dependence in conformal transformations in ADS isometry from boundary theory. So this is our motivation. So in short, what we can tell is, maybe instead of from top, we should read from bottom, radial dependence in ADS isometry. And this is tied to the fact that scale dependence of symmetry transformation in the boundary, which we will see next. This will be the part of talk, and this is ultimately comes from scale invariance of boundary Wilson action with RG scale. Okay. So this comes to the topic Wilsonian form of holographic RG. We will do this by studying this. So first I'll just spend a few words, people who don't know maybe Wilsonian picture of renormalization. It is like Adolph's scheme of perturbative renormalization is replaced with Wilsonian picture, where high momentum modes are integrated in order to obtain a low energy effective action. So this is performed in the exact RG formalism. This is performed by including an analytic cutoff function in the kinetic energy term, which suppresses the high momentum mode smoothly. So then people find the flow of this low energy Wilson action, which is expressed in terms of an integral differential equation, which is called exact RG equation. The name exact comes from the fact that any physical observable like correlators at their scale at any point of time point of scale can be obtained from the low energy scale. Yeah. So the flow equation, it can be of action also, it can be of effective action also, generating function also. So that will give rise to different versions of exact RG equation. In this talk, we will consider Polchinski's version of ERG equation, which is flow of interacting part of Wilson action. This is the version which is most suitable for the holographic RG or to explain holography. So this equation can be written as diffusion equation. This will be mainly used in our talk. Okay, so whatever I told, just written mathematically. First of all, this lambda, t and z, these are all RG scale I am using. T is RG scale and this lambda naught is just UV cutoff. For continuum theory it is infinity. This is the relation, and z is equal to e to the power t. This is also RG scale, but in ADS, when we will go to ADS action, refer to ADS action, we will use mainly this variable z. Yeah, so Wilson action is given by this following expression. This is like all the non-trivial facts that higher momentum modes has been suppressed. This is hidden in this term. This is SIT, interacting part of the Wilson action, and this is the free part or kinetic energy part. You can see that we have used a function, cutoff function, which is chosen analytic. So functional form of this cutoff function is k by p to the power 2 nu. Okay. This g or k interchangeably one can call cutoff function. For example, one can take a cutoff function which is of the form e to the power minus p square lambda square. But in this work we have not taken any form like form of cutoff function. Yeah. So after we have this Wilson action, one can find Polchinski version of ERG, which deals only with interacting part of SIT. So this flow of the action is, we define a flow of this quantity psi, which is of e to the power minus SIT, and then if you find this equation, it becomes like a diffusion equation. So when you have diffusion equation, this is the equation we will use in our talk. Yes, sorry, nu is like for free theory it's 1, like this anomalous dimension. So now I will just tell a bit that how holography from boundary exact RG. This like from UV-IR duality, we know extra dimension in the bulk is scale in the boundary. Hence, the evolution of radial dimension in the like ADS should be related to the RG evolution of the boundary. That means the evolution, this means like evolution operator of Polchinski equation can be mapped to bulk ADS action by certain field redefinition and choice of cutoff function. So this was first established using Polchinski equation of the paper Bala and Sonoda in 2018 for Polchinski equation, for 2019 for flow equation of generating functional. It is to be noted that choice of cutoff function is unimportant in the boundary field theory. So from boundary field theory side, different choices of cutoff function merely changes the reparameterization or the renormalization of the field, but a certain choice of the cutoff function remarkably gives rise to the bulk ADS action. Okay, so this is the main essence of what we will use in our talk, and just evolution operator of Polchinski equation. This is like a diffusion equation. So evolution operator will be like g dot double derivative of phi, but in order to make connection with bulk action, we need to go to functional formalism. So that is like we find this Hamiltonian actional functional corresponding to the Hamiltonian by doing Legendre transformation, and then first rotating to Minkowski space and then back to Euclidean space, because we will be using Hamiltonian formalism. The main equation which is the result is we will act with this evolution operator on the Wilson action at some initial scale at the scale Ti, and we will get a Wilson action of final scale Tf. So this is like we will interpret this as a ADS action, but this form is not yet in ADS action form. That will be done by certain mapping. So this map is, this is three things: scale to Poincare coordinate, that's the variable z, and then field transformation, field redefinition by a factor f, which is a function of cutoff function, and then a choice of cutoff function, such that so this becomes free ADS action in Poincare coordinate. Okay. So this is the map we will use. Yeah, so this is the scheme. This is I have shown for free theory, free ADS action. Okay. So this scheme was further explored for the bulk action, for vector boson and graviton with leading interaction term, for Yang-Mills theory with cubic interaction term in ADS4. Also some aspects of Wien action in flat space and BSCFT, a series of papers with me, my junior Pawan, who is in audience, Bala, from 2021 to 25. Yeah. So we give further credence to this formalism by studying symmetry group of the evolution operator. Because the evolution operator is mapping to the ADS action, so it is expected that the same map will also take the transformation laws to ADS generators. So we have shown that symmetry transformations from the SO1 D+1 group for any choice of cutoff function, and this group is, although it is SO1 plus D+1, these are non-standard conformal transformation. That means they have scale dependence. So this is the origin of, we will see origin of scale dependence in the ADS isometry. Okay. Okay, I just sum up all these things. What we will do first is we have this action function in variable phi, then we have transformed it with respect to y. So there will be two action functional, one is s phi and one is sy. We will find symmetry transformation of both these things, and then we will put the choice of cutoff function. It will reduce to the ADS isometry. Okay. Now, given all these things, what is the meaning of all these things from the boundary side? So boundary side, we will see this is tied to the fact that Wilson action scale invariance or conformal invariance of the Wilson action. For example, if we consider condition for scale invariance of Wilson action, this is given by this condition, where this is the scale transformation psi is e to the power minus s lambda. So this equation, if you see, even for free theory, if you put only k is equal to 1, this is satisfied. Otherwise, it is not satisfied, because it is not satisfied for any finite scale. So when we have a finite scale or finite cutoff, then e to the power s lambda evolves with lambda. Then we also need to replace this field phi and this function, all the function of field phi, with the composite operator. What is composite operator? That is like we need to replace this full sigma operator with this bracket notation I have used, which is like we are evolving with the evolution operator of Polchinski equation. That means we need to find how these operators are getting evolving with RD scale. For example, composite operator means for phi composite operators is here phi by k, 1 by k by k, this form, and composite operator of del del, sorry, this should be del del phi is kp this. So when we are in continuum physics, k is 1 and then it's just usual operator. So all these things we need to replace here, all this with this function, so phi with composite operator, and it can be shown that the scale evolved version of this above condition is fixed point ERG equation. So when we replace with composite operator, this is actually fixed point equation. So that is the reason these composite operators are there, and that's why these symmetry transformations have the scale dependent part. So similar reasoning should hold for special conformal transmission, but it is not straightforward to understand. Instead, we have derived that explicitly. So given the fact that we have scale dependence in the symmetry transformation of Wilson action, then I will just go back to this functional formalism equation. Like this is like when the theory is in fixed point, then this evolution action will not change form of the field. So it is expected that whatever is the symmetry of the fixed point Wilson action, that at least will not be broken by this bulk action. So whatever is the symmetry of the Wilson action, that same symmetry group should be kept by this bulk action also. So that's why this bulk action for any choice of cutoff function, it have this SO1 D+1 group, and on certain choice it is becoming just ADS isometry. Okay, this is the physical argument of what I want to tell. Do anyone have any question? Okay. If not, I'll just tell what is the details of computation. Okay, so only input we have used properties of cutoff function. This is the functional form k by p to the power 2 nu. Nu is 1 for free theory, and this gives rise to two properties of cutoff function. That is like, because our p is only like depends on absolute value of p, we can interchange this indices while derivative, and there will be some variant of this this relation also, and then there will be suitable scaling relation of this cutoff function. This can be done for any functions of cutoff function. So that's the only input that using these properties one can perform all computations indicated in this talk. Yeah, so first is scale transformation in phi. We start with the usual scale transformation. This is the answer. Then if you put this on this S phi, you are left with this term. Then if you add this scale dependent term, you are left with one boundary term in T, and then this one cancels this one. Okay, so this boundary term is like one can find Noether current from that boundary term. In momentum space, this gives to Hamiltonian because this is at the time, so this will give a Hamiltonian as expected. So except that boundary term, we have this scale transformation. Note that this is, we just give physical argument that this is consistent with this one. This also have lambda del lambda, which is del T. Okay, so this scale transformation is easy to derive. This special conformal transformation requires more care, but anyway, I have written the result that action of scale dependence special conformal transformation can be obtained by using properties of GPT. For example, I have taken only scale independent part first, that gives this expression. Then we propose further scale dependent transformation. So these are two parts. One is scale dependent, another is also dependent on cutoff function. So these two parts cancel this part and give one boundary term. This boundary term usually can give rise to Noether charge corresponding to conformal charge. So except that, we have invariance under special conformal transformation with this transformation, but the last part is dependent on the cutoff function. Okay, so then S1 D+1 algebra, this modified, this is for symmetry transformation in phi. So this modified C mu phi and D phi we obtain along with other conformal transformation forms a S1 D+1 group. This can be proved using properties of cutoff function. We also confirm the same in the Hamiltonian formalism, for which I'll spend one slide. It's more natural way to see scale dependence in conformal transformation. So to use Hamiltonian description, first we go to Minkowski space. And if you remember form of S phi, that is like phi dot, okay, phi dot phi dot. So this is not Lorentz invariant, so that test tensor will not be symmetric. But the special conformal transformation can be constructed by these two parts. Like one part is usual one scale independent, and this one is a RG time supplemented part. This part 2. So part 1 gives the usual commutation relation, and part 2 gives this correction to the deletion. That is like Z, HZ. So HZ we can tell this as Z del del Z. So this is correctly giving modification in scale transformation also. And if you take this part and act it on field phi, then it reproduces these two parts of this conformal transformation. So it is easier to see scale dependence of conformal transformation in this Hamiltonian formalism. Yeah. Also, then next we go to bulk action in Y. So transformation of bulk action is Z is equal to e to the power t, field redefinition, and we are not making any choice of cutoff function f as of now. So if you do that, this bulk action in Y takes this form where C is a function is defined, which is a function of cutoff function. Then modified scale transformation, it can be shown, it will be same as S phi. But the conformal transformation in Y, we apply, suppose this answer, we sort of understand that this 4 will be same, the last part will be is dependent on cutoff function, that will change. So if you apply this 4 transformation on Sy, you are left with this term, and then to accept the boundary term, you can cancel this term using this 5th term. Okay. So then special conformal transformation for Sy is this have, the last one is dependent on cutoff function. So C is this function, and one can check consistency of C mu phi and C mu y by using field redefinition. Field redefinition of between phi and y. Okay, now how it maps to like ADS isometric? Because we map bulk action to ADS action by putting this thing. This is the part we will put it as ADS. So we need to put, if you compare, we just need to put C pz is p square plus m square z square. So if we put in here C is equal to p square plus m square by z square, we are exactly like left with ADS special conformal transformation. So with all these things, we have other things are not scale dependent, these two will change, and the same map which maps from bulk action to ADS action, evolution operator to ADS action, maps symmetry transformation laws to ADS isometry. Okay, so that is the end of my talk. The conclusion is we have shown the symmetry transformation of the evolution operator of Polchinski equation form SO1 D plus 1 group with non-standard conformal transformation for any form of cutoff function. The same map which transforms the evolution operator to bulk ADS action map this modified conformal transformation to ADS isometry. So other thing what we have done is instead of considering Polchinski equation, one can also consider ERG equation for full Wilson action. That also can be rewritten in the same form as Polchinski equation. So that also inherit the same property, same group SO1 D plus 1, but with suitably changed conformal transformation. That is also will be included in our paper. Okay, and then several natural future directions that if it is can be done for Polchinski's version, can it be done for other versions of ERG equation. For example, this Wetridge equation is used a lot in functional renormation group. Can one find symmetry group for this evolution operator of this equation? And then like when we talked about that this bulk action, this evolution operator can be mapped to graviton action that actually correspond to ERG equation of stress tensor, composite stress tensor from the boundary, and then map to graviton action. So what will be those kind of ERG equation consist with composite operators? Can one find symmetry group of evolution operator of those actions? And also at the end, like can we interpret symmetry group of other non-ADS bulk theory in this using this formalism? Okay, thank you.
Questions for Shrimanti?
Independent of the choice of the cutoff function, you always have the symmetry. Why is it when you can, if you choose to, if you choose a cutoff function which explicitly breaks symmetry, or is it not possible to find?
No, it is not possible.
Meaning, if you
So-
want it to be a
No,
cutoff
no, no.
function, then it will have to have the symmetries. Eh?
No. Can you tell again?
What I'm saying is that can't you choose a function which explicitly breaks the symmetry because of
No.
the way?
It is not possible because it is tied with, I'm just telling you, it is tied with this equation. This is Polzinski equation in functional formalism. So this is like, if you start with a fixed point action, it will be like, it will be same, like it will not evolve anything. The scale will be there, but action will not change.
So you have other conditions that you want the form of this to remain the same. And
No, it is just fixed point action. Fixed point action will be
no,
like
I'm saying
this.
is that in the choice of the cutoff function, you're demanding something else, that it has to satisfy the form of this equation, for example, right? When its cutoff function is just a function of momentum, so why is it not possible to choose a function? Forget about the cutoff, just a function which breaks the symmetry. It's
Yeah, that is like explicitly we are checking because we are using only this property, which is means it has to, any cutoff function have to have this property. So that's why it is not. Yeah, it's explicit. Like we have checked everything.
thanks.
Any other question? Let's thank Shamanti again for her talk. So now we'll have the last talk of the conference, online mode, by Shubhranil. I hand over the chairing responsibility to him.
Thank you. Yeah, just 5 minutes. We'll just set it up.
Yeah, this one. And subject. Google Meet.
Yes.
Okay. Welcome.
Shubhranil, can you hear us?
Yes, I can hear you. Can you hear me?
Yeah, please share the screen.
Okay, can you see the screen?
Yeah. इसको छोटा नहीं कर सकते इसको इसको छोटा नहीं साइड नहीं जा रहा ऊपर उठा रही Okay, Shubhranil. So our next speaker is Shubhranil Chakraborty, and he's going to speak about manifestly duality symmetric action, a stringy perspective.
Okay, thanks, Abhishek. So let me start by thanking the organizers. First and foremost, it's a pity that I couldn't be there in person, but the travel situation was beyond my control. So I missed meeting a lot of my old friends and colleagues and seniors. but also thanks to the organizers for rearranging my talk at such a short notice. So let me start. So this talk is going to be mostly based on this recent preprint written by my long-term collaborator Madhusudan Raman and Arkajyoti Manna, and an upcoming work which we hope to be finished by end of this month so that it can be on archive definitely early next year. And it's part of a slew of long list of work that I have been personally following for last 4 or 5 years. Most of these works have Madhu or Arko as a collaborator, and some of these papers also had the Divanshu Gupta, who was a student, master student at IMSC, and Aviral, who is a PhD student at Masaryk, as a collaborator. So let me start. Quantum field theories with self-dual field strengths are of interest for various reasons. In fact, I don't think I need to convince any of the present audience, because these theories are also intimately related to what are called electromagnetic dualities. And essentially, the idea is that if you have a self-dual bosons and you compactify it on a torus, then the resulting theory is usually something that exhibits electric and magnetic duality, even in presence of sources. And these theories are ubiquitous within string theory. So type 2b supergravity has a self-dual RR5 form flux, and anytime you do any dimensional reduction of type 2b, it will naturally lead to some QFT with or without gravity, which will exhibit either electromagnetic duality or self-duality. So string theory provides a very natural way to work with this class of theories. This approach is usually called Sen's formalism, because Ashok Sen was the one who pioneered this approach way back in 2015 and a follow-up paper in 2019. And the stringy approach is by far superior to any other approaches to these quantum field theories, and it clarifies a lot of apparent paradoxes and confusions that have plagued the community over the last several decades. I'm sure all of you know that a standard action, Lorentz invariant polynomial action doesn't exist for this type of theories. That's the usual textbook lore. But for last 10 years or so, there is a viable alternative which is much more powerful, which is inspired by string theory, which is called Sen's formalism. So a very quick summary of Sen's formalism. So this yields a manifestly Lorentz invariant, duality invariant, polynomial, and quantizable action. All these points are very important because, as far as I know, there is no other formulation which ticks all of these boxes. You can have something which is duality invariant, polynomial, etc., but it won't be manifestly Lorentz symmetric, and so on and so forth. So Sen's formalism is the only one that does all of this so far. And the action looks something like this. You have, so let me talk about self-dual bosons in some 4n+2 Minkowski space-time. So this Q is the one that we are after. This is the one which is self-dual. P is an extra field. Its role will be clarified shortly. And phi is any other physical field with which you want your self-dual degrees of freedom to interact. Okay. So any other physical field with which the self-dual fields can couple, I'm representing by blanket label phi i's. So this Q is defined to be self-dual, and importantly, it is not to be thought of as a field strength of a potential. So in Sen's formulation, there are several a priori strange features. One of the first one is that you have to introduce an additional field P, which we can show that it completely decouples from the self-dual field Q. And you need to do that to write down a Lorentz invariant kinetic term. But you also need to describe the self-dual degrees of freedom by treating the field strength of the flux as the fundamental field and not the gauge field. So there is not going to be any notion of a gauge field that is invoked within Sen's formulation. And the RR flux itself is treated as the fundamental object. And the interaction Lagrangian is, it can be anything as long as it satisfies all the symmetries. The only restriction you need to put is that you cannot have this extra field P appearing on this interaction Lagrangian. And with this, you can actually prove, as Sen proved, that once you quantize this action, the Hilbert space containing only the extra degrees of freedom completely decouples from the rest of the physical degrees of freedom. So you can just, even though this action looks like there is a kinetic mixing, it's actually artificial. And you can always focus on just the physical part of the Hilbert space and forget about the extra degrees of freedom. And this decoupling is rigorously seen in the Hamiltonian framework. It's harder to see in the coordinate space action, but if you go into the Hamiltonian framework, you can see this very rigorously. So this is just a very quick one-slide summary of sense formulation. And it has seen a lot of success stories over the last 10 years or so. So first and foremost, this has been used for type 2b supergravity on 10D, 6-dimensional supergravity, M5 brane wall volume actions, 2D chiral bosons, all sorts of things. But I will argue that the classical solution is not the acid test, but doing quantum computations is. So I'll just give a list of some quantum computations that has been done in this formulation to great success. So one is that you can actually derive the famous Alvarez-Gombe-Witten gravitation anomaly computation, but this time you can actually derive it. Remember, Alvarez-Gombe-Witten proposed a set of Feynman rules to compute the gravitational anomaly of the chiral bosons. But here, starting from sense action, you can actually derive the Feynman rules, systematically do the one-loop anomaly computations following textbook methods, and you can recover the results. You can compute the partition function. And of course, we know independently that partition functions of chiral bosons are supposed to be that of a Chern-Simons, whose boundary contains the chiral bosons. And this is something that Andriolo et al. Showed in 2021. And me and my collaborators, we showed that if you do a one-loop computation in a TT-bar deformed some number of chirals and some number of antichiral bosons, you actually get the precise answer that the TT-bar deformed general prescription predicts using sense formulation. And finally, this year, we use sense formulation for 4-dimensional quantum electrodynamics in presence of magnetic monopoles, and where there has been some apparent paradoxes and confusions over the last several decades. And we show that all of them gets resolved extremely straightforwardly following just textbook QFT if you start from sense action. And also this year, Mamade and Zuibach in a very nice paper showed that this is actually the sense action is what you get as the action for supergravity if you start from the string field theory, the space-time action of string theory, and you take the low energy or the alpha prime goes to 0 limit. So these are all the success stories. But are there room for improvement? And I would argue that there is a small room for improvement, but a crucial one, and which is going to be the focus of today's talk. And the first point that I want to make is that despite this huge success, working with field strengths is quite unusual and often tricky. So for example, if you want to introduce sources for the field strengths, these cannot be the usual currents, but a surface attached to it. So usually we would think that there is a current, this bold arrow, which is J, and there is a gauge field that couples to this J, the wall line of a moving charge particle, say. Here, instead, you have to think that there is a surface which has only one constraint, that this surface has to be, one end of this surface has to be glued to the wall line of a charge particle. Otherwise, this surface is free to be extend in the other direction as it likes. And the relation of this surface, denoted by this 2 tensor, which is an antisymmetric form, is essentially this, that del mu sigma mu nu j nu. And you see that any conserved current can be written like this, at least locally. This is just the Poincaré lemma. And this sigma is going to act like the source for the field strength. So not the J, but the sigma. And this is a bit unusual because when we express the current sources in terms of local fields, this J is something that can be constructed easily in terms of, let's say, fermion bilinears or complex scalar fields and so on and so forth. If we want to use those fields to express sigma, you can understand that there will be some sort of non-locality, which is, of course, a little artificial, but at some intermediate steps, the action and the formulation will look non-local, and it might be a little subtle, and it might be a little tricky.
So
another point is that, yeah, sorry, go on.
So is the sigma mu nu just the Dirac string?
You can think of it like a Dirac string, but the point is that it doesn't have to be. Like let's say if you have just electric charge particles, right? So
that would have a Dirac string for the dual vector potential.
Yeah, exactly. It would have for Dirac string for the dual formulation, but even if you stay in this the electric formulation, you can still define the sigma mu nu. I'm just simply saying that any conserved current, you can always write it as a divergence of an antisymmetric tensor and think of the sigma mu nu extended like this. Okay. So another point is that Wheaton effects, which you know is essentially turning on the CP violating theta term, this F wedge F. This is difficult to realizing using only fluxes, because you see F wedge F is a total derivative term only if you're allowed to think of the field strength as a field strength. So if F is equals to dA, then F wedge F is a boundary term, so it doesn't affect the dynamics, but it has some other effect which we know is shifting the electric charges of the magnetic monopoles. So this is very difficult to realize if F itself is the degree of freedom. So F wedge F is no longer a boundary term, but it's a quadratic term and it alters the theory. So that's a bit tricky, and we know that Wheaton effect is definitely a viable effect. It has to be there has to be some mechanism to generate this, and it seems quite tricky. I'm not saying that it's impossible within sense formulation, but it seems a priori not obvious how to go about doing it. And finally, the stringy arguments for this whole sense formalism actually doesn't only apply to the self-dual RR 5-form flux, but to all of the RR fluxes. And this seems a bit weird because, of course, for type 2b, you might not have a standard textbook action. But for type 2a supergravity, nobody ever complained that we don't have an action. We have a perfectly well-defined action. Everybody learns it in their textbooks. And that is something that can be expressed completely in terms of the Raman-Raman potentials. Then why does the standard supergravity action work so well for the other RR fluxes? Whereas the string theory says that, you know, somehow when you come from the string field theory side, you have to somehow have the fluxes being more fundamental and not invoke the potentials at all. So I hope that these arguments would convince you that sense action with potential or gauge fields might actually capture the best of both worlds. So if somehow we can keep all the features of sense action, that it's nicely Lorentz invariant, polynomial, it can be quantized straightforwardly, the duality is manifest. But if we can relax this demand that we have to work with field strengths or fluxes as fundamental, then it might be really something that help us reconcile a lot of this tension between the standard supergravity approach and the standard string field theory approach, as well as allow us to resolve these puzzles as well. So I'm going to tell you that, yes, this is possible. And to motivate this, let us take a step back and ask one very basic question, which might be too elementary for some of you, but I promise you that this is worth it, that what decides that the correct field strength? So for example, let's say in some dimensions, I have decided that I have some sort of U1 field theory, and there is some potential, and I write down the simple standard Maxwell action. So DC weight star DC, nothing else. Now, I know that C has a gauge invariance, a U1 gauge invariance, and I want my theory to be gauge invariant. So I know that whatever is the definition of the field strength has to be gauge invariant. And of course, let's say that from dimensional arguments, I have also argued that it has to be first order in derivative. But this alone does not fix what should be the field strength. So just demanding that there is a gauge invariance and it's first order in derivative cannot uniquely fix that it has to be the field strength. It can be, so for example, it can be DC, or it could be star DC, or it could be any linear combination of these two. Both of these, all of these possibilities have the features that they are gauge invariant and they are first order in derivative. What actually fixes the definition of the field strength is in absence of the sources, there is a higher form symmetry or a generalized symmetry, which if you demand, that will fix what is the correct definition of the field strength. So for example, in the standard formulation where we think of DC as the field strength, which I'm denoting by F sub E, the E stands for electric, let's say, we can demand that there is an electric higher form symmetry, which is that delta C changes by a closed form. And then this singles out that if I demand that this has to be this higher form symmetry has to be a symmetry of the theory, then this singles out that this is the correct field strength. Similarly, you could do a dual description. You can define the magnetic field strength as your correct field strength, and you can shift the dual. You have a magnetic higher form symmetry where you shift the C check by some closed form. Then it would have singled out the magnetic field strength or the dual field strength as the correct definition of the field strength. And you see, either of the symmetry, electric or magnetic, has the feature that once you have demand this, it automatically tells you that either Fe or Fm will satisfy the Bianchi identity. And then, of course, there is the dual field strength tensor, which will have the dynamic equations of motions once you turn on the sources. And this is problematic in case of self-dual, because in the self-dual cases, there is no difference between Bianchi identity and the equations of motion. So clearly, we cannot impose either of these higher form symmetries, because if you do that, then you have a Bianchi, but then the self-duality will force that Bianchi to become equation of motion, and that is the root of all the problems. And so our claim is that the correct higher form symmetry that you should demand to define the correct field strength in case of self-dual or electromagnetic dual invariant theory is neither electric nor the magnetic higher form symmetry, but what we call a harmonic higher form symmetry, where we demand that the C changes by d dagger of some small f, and this small f is defined to be self-dual and harmonic. Once you do that, it uniquely singles out some f as a field strength, where f is this unique linear combination up to an overall irrelevant constant. Once you have this, you realize that under this symmetry, the Maxwell's action changes by a total derivative, which under normal standard boundary conditions you can ignore. And you see that even the free equation that you get from here, d star dc equals to 0, you can cast it as a free equation of a self-dual field strength, where this is the self-dual field strength is defined to be this f. So at this point, a natural thing to ask is that this action, can I just express, instead of using the DC, can I express it in such that it's expressed in terms of this correct field strength itself? And the answer is yes. But to do that, you have to leave this safe haven of Maxwell-like action, and you have to do precisely what Sen did for his formulation, that is to introduce this extra field. So this is what we did. So in this paper, which we call a new action. So let me describe the flat spacetime bit first. So the free action reads like this. And you might say that, okay, this looks precisely like Sen's action, but there is a crucial difference. F is now not a fundamental field. F is expressed in terms of a gauge potential in precisely this manner. So this is a definition of F, that F is defined to be DC plus star DC. So the action actually should be thought of as so P is a dynamical field, C is a dynamical field, and this is the correct action. And the equations of motions for the extra field is this, and then for the actual field is d star dc equals to 0, which in terms of the field strength you can write as d star f equals df equals to 0. And now you have to realize that df is not identically 0. Both of these are equations of motions which are dynamically true only on shell. Neither of them are true off shell. So that's the crucial improvement. And you have a perfectly Lorentz invariant, duality invariant way of deriving these things using potentials. And it's very easy to now turn on the sources. And unlike the Sen's case, because we have a potential, we can turn on the source just like the textbook case. We can just simply couple it to the standard current to and form like this. And you have precisely the correct equations of motion that you would expect a self-dual field strength to have in presence of some sources. So this new action, and so let me just tell you that what is the connection of this new action with the Maxwell-like action. So this new action has a total derivative term, which is this one. So now if your spacetime is flat, you can safely ignore this total derivative term. And then you can integrate out P completely. You just define a new field, P minus C, and you can integrate this out completely. So you complete the square and just the P minus C field completely decouples. So you just integrate it out. And what you are left with is precisely the Maxwell equation in presence of a source. But this Maxwell-like equation now works because the correct definition of the field strength is not just DC, but DC plus star DC. So note that there is no by-hand imposition of self-duality like the pseudo action. So pseudo action is also like this, but there you think of the field strength as DC. So therefore, you have to impose that DC equals to star DC at the level of equations of motion. We don't need to do that here because the correct definition of the field strength is not DC, but DC plus star DC. And this is reminiscent actually of earlier approaches by various people. The two famous ones that comes to mind immediately is one by Dirac when he wanted to incorporate the monopoles. And he realized that he cannot define the field strength to be D of A anymore. and he defined it to be dA plus some star of sigma. This time, this sigma is indeed the wall sheet of the Dirac string. Another approach was by Zwanziger in the 70s when he introduced this two potential to describe QFT with monopoles. And he declared that, okay, I have two potentials, which he called A and B. So the FA and FB are the two usual field strengths associated with the two U1 potentials A and B. But he declared that the correct field strength is neither FA nor FB, but this combination, and it's dual.
So, Subramanian, sorry to interrupt. So you have about 10 minutes. Okay.
10 minutes?
Yeah.
Okay, thanks. Yeah, so this definition of modifying the definition of field strength is definitely not without precedent. But what we are arguing is that you do not need to, unlike Dirac or Zwanziger, you don't need to ad hoc say that, okay, this is the definition. There is actually a symmetry principle that identifies that what is the correct definition of the field strength. Okay, so we have this new action, which is expressible in terms of potentials. So this has a chance of looking much more like supergravity. How does this connect to the stringy approach? How does this connect to the Sainz formulation, which we know that comes directly from the string theory? So we see that we have this action, and this action has this higher form symmetry. It's a global symmetry, which we call harmonic symmetry. But we know that string theory is not supposed to have any global symmetry. So if this action has to sit nicely within string theory, we have to somehow find a way that this higher form symmetry should be gauged. And you can check that there is no obstruction to gauging this higher form symmetry. So we can happily go about gauging it. So if we gauge it, that F goes to some F hat, which is F plus some H, and H is self-dual because it has to respect the self-duality condition of the F, then you can essentially see that we can relax this condition that F has to be harmonic. Instead, we can say that this background gauge field H now transforms, and simultaneously when C transforms by this, the background gauge field transforms like this. And we can see that this F hat is perfectly gauge invariant. So you can gauge this higher form symmetry like this by introducing a background gauge field, the standard trick. And we can show that this shifted field strength F hat is now perfectly gauge invariant. But now let us take a closer look at this shifted field strength. What is this shifted field strength? This is nothing but F plus H. And F, remember, it was DC plus star DC plus H. And now H is a self-dual two form. It will have an exact piece, it will have an co-exact piece, and it will have an harmonic piece. The exact and the co-exact piece you can just absorb into redefining the C. So you might as well take H to be just an harmonic two form. But then this is actually nothing but just the Hodge decomposition of a generic self-dual 2n+1 form. And if you have an action, so if in this action, if you just replace F by F hat, then essentially varying the action with respect to C and this background gauge field H both is actually nothing but varying a total 2n+1 self-dual form, which is precisely the Sainz action, with a field strength being treated as fundamental. So the general lesson is that if you take this harmonic higher form symmetry and you gauge it, you land precisely to the Sainz formulation. Okay, so you might say that what is new? So far, it looks like, everything is just, either Maxwell action or Sainz formulation, but not quite. There are several things which are new. First is that this new action you can extend to any duality invariant theory in D dimensions. You can do it very straightforwardly. I'm focusing on self-duality for time constraints, but you can do it for any other dimensions. You can derive the Feynman rules from this new action, and it can be mapped to Sainz. So basically, our action is potential-based, a standard action, but you can rearrange this perturbation theory as a field strength-based perturbation theory, and that up to a field redefinition is identical to the Feynman rules that you derive from Sainz action. So all amplitude computations that are done in Sainz formulation, all quantum computations, are naturally subsumed in this thing. But on top of that, we can actually now incorporate Witten effect or dual if Witten effect very easily. You just turn on the DC wedge DC kind of term in the action. And it is also possible to write down explicit matter currents in terms of local fields, because our source term is just a standard source term. So we do not have to do anything extra. There are no need for turning on non-local sources. you can just turn on the standard fermionic bilinears or scalar field with complex scalar fields kind of currents, and that will be perfectly fine for this. And this is something that I will not explain in this talk, but you can take a look into our papers. The supersymmetrization of sense formulation is possible, but it's actually quite tricky. So you have to do it case by case basis. But now in this new action, supersymmetrization is very straightforward. It just works like the textbook theory. So if you know how to supersymmetrize anything like a Maxwell theory, you can supersymmetrize this action as well. But the greatest point, I would say, the greatest advantage for this new formulation is this, that we can now extend this construction to non-abelian gauge fields, which I do not know how to do in sense formulation at all. So let me explain that. And I'll explain it in the context of self-dual Young-Mills, which is, of course, something that is extremely important and prevalent in literature. So the idea is that suppose we are in D equals to 4 Euclidean now, so that we can have a real self-dual Young-Mills gauge field. And I will just simply write the Young-Mills action like this. The kinetic piece, I have separated it out, and all the cubic and quartic self-interactions are clubbed into this term L-int. With this is the claim. The action, the new action for the self-dual Young-Mills is this, that B plays the role of the extra field, and this L-int is precisely this L-int. And with this action, you can show that ignore the extra field. The extra field will satisfy its completely decoupled equation of motion. We are not interested in that. The physical gluon field, the A, will satisfy these equations, where this F is actually nothing but a self-dual combination. So FA is basically the covariant derivative of A, the usual definition of the field strength. So it's essentially FA plus star FA. And this is nothing but the self-dual Young-Mills equation, but this time we can derive it from an action. And it's precisely this. There is no other contribution. No anti-self-dual part of the Young-Mills field will leave on shell. And this definition of field strength, you might say that how did we come up with this thing? Once again, there is a generalized symmetry that fixes this. There is a non-abelian version of the harmonic symmetry which fixes this thing, that if I change A2 by some covariant derivative dagger lambda, where lambda is self-dual and it is covariantly closed, then you can show that the unique definition of the field strength which respects this higher form symmetry is this one. So we demand that the action has this symmetry, and then that fixes that this is the field strength. And in terms of this field strength, these actions, equations of motions are precisely the self-dual Young-Mills. And now the point is that, of course, I focused on self-dual Young-Mills because it's familiarly known in the literature, but you do not have to. It is possible to do this in Lorentzian signatures and with two non-abelian gauge fields. So you just, turn on two different gauge fields, A and A check, and you can have some electromagnetic dual-like duality, but now this time for Young-Mills. And this is something that seems very new to us. The Young-Mills, the modified Young-Mills equations that you get, the action that you get looks very different, looks very new. At least we have not seen them in literature before, and they look very exciting. Another point is that it can also in principle work on higher dimensions, except that in higher dimensions, non-abelianness is not captured by gauge groups, but what are called higher gauge theories. So if you tell me what is the higher gauge structure, one can actually do this whole thing in any general dimensions. So it seems very exciting. And now you see that this is something which would have been very tricky to do in sense formulation, simply because if we are working with field strength, then we do not know how to capture this cubic and quartic self-interaction of gluons solely in terms of field strength. That doesn't seem like very plausible.
Okay, Shubhanil, you have about 5 minutes.
Yeah, okay, thanks. Okay, so at this point, some of you might be asking that why we need the extra field, because it seems like, you can just start with the Maxwell or the Young-Mills, and you can just use the correct definition of the field strength. So forget about the extra field, just work with familiar actions. Just remember that the definition of the field strength is not the curvature of the potentials, but these things that are fixed by the harmonic and symmetry. And there is a very good reason that why you need the extra field. One is, of course, string theory tells you that it has to have this extra field because that's the correct low energy limit. But even without that, the coupling to gravity is actually very tricky if you start with Maxwell or Young-Mills-like action. So let me show you why. So suppose you start with the Maxwell-like theory, and you say it's in flat space time, and you say that, okay, fine, I will minimally couple it to gravity. What you do, you replace the star by star G, and you integrate over this manifold. And you will end up with this action. Everybody knows this thing. But once you do that, there's something that undesirable that has happened, which is that this total stress tensor now has a contribution from the self-dual part, but it has also has a contribution from the anti-self-dual part. So there is no way to couple this to gravity minimally without turning on the anti-self-dual part. And you do not want that. Suppose you want a theory of only self-dual fields coupled to gravity. So either you say that, okay, it's impossible, or you say that, this is not the correct way of doing it. So for some time, people actually thought that this was impossible. But of course, the correct answer is that you do not couple this theory to gravity minimally. And there are good arguments for that. One is, of course, that comes from string field theory, as shown by Mamad and Zwieback. And in fact, this was known in string field theory community for a long time, but it has been shown explicitly at the supergravity level by them earlier this year. But also, this was expected from general grounds, which was pointed out by Witten in his geometric Langlands paper, and recently explained very well by Neil Lambert in an overview of how to get 2,0 theories and so on and so forth. So this is actually same situation and sense, and it's the same solution. So because I am short on time, I will just quickly argue what is the solution. The solution is that essentially you treat gravity like any other interactions. So essentially you couple gravity not by turning any of this to star by star G and integrate over manifold, but you just include gravity in this interaction term. So you think of phi as gravitons, and you write down a suitable interaction term of the self-dual field C with the gravitons. And the way it is done is basically by a linear map MF. And you note that none of these integrals include the curved metric as the measure factor. The metric enters this action only via this linear map M of F. Okay. And this M of F has the property that the desired self-dual form on the curved background is actually Fg is equals to star G Fg, which is defined as F minus MF. And the whole question is that, can you construct a linear map which guarantees the above results? And the answer is yes. So Sen gave an independent construction, and Neil Lambert and his collaborators gave an independent construction. So I thought I would explain this construction, but since I'm short on time, let me just tell you that it is possible that there is an explicit formula for this M you can find out for any background. And the only thing that you need to generalize is that this construction needs to be extended to any dimension in any P form, and also for Yang-Mills case. And I mean, this is being done, and there seems to be no problem. And we hope to report this very soon, in a matter of few weeks. Okay, so with this, let me summarize. The idea is that there is a new action which retains all the benefits of the stringy formulation, which is like maintaining manifest Lorentz symmetry, manifest duality, and an action with which you can do standard QFT to address duality symmetric theories. And it's related indeed to the stringy action by simply that there is a harmonic higher form symmetry which this new action has. If you gauge that symmetry, you end up precisely with the stringy action. On the other hand, this action has a total derivative boundary term. If you ignore this boundary term, you can integrate out this extra field trivially, and you end up with the Maxwell action. But this does not lead to Maxwell theory, because remember, this theory has a definition of a field strength that is inherited by the Maxwell action. And that definition of field strength, in a very subtle but simple way, ensures that this action still describes a duality invariant theory. So I'll end with some open questions. That we have to understand this harmonic symmetry from the Chern-Simons perspective, because it has been well known that self-dual bosons are related to the Chern-Simons theory. And of course, whenever you have these higher form symmetries, you need to have a symmetric TFT understanding of the symmetries. And this is something that is ongoing work with two of my collaborators in Europe. We also need to understand the role of the boundary term. If you're not in a space-time where the boundary term can be easily ignored, then this can potentially signify a new source for boundary terms in string theory. So some of you who have been following the SFT literatures, you might know that on-shell actions, the space-time action of the string theory on-shell is supposed to vanish unless you supply it with some boundary terms. And it seems like this is a new way of getting boundary terms, which was not noticed before. We also need to understand the wall sheet origin of this higher form symmetry. Like, I mean, how do you sort of see in different picture sectors that what is this happening from the wall sheet perspective? But in a related way, a more exciting direction to pursue would be to have a first principle understanding of the Hilbert spaces of this theory, starting from the action, and understanding the non-abelian case with two gauge fields looks very intriguing. It's a very new and exciting QFT, so to me it seems like something that should be studied in more details. And in principle, multiple M5 ring wall volume action is supposed to have some sort of non-abelian higher gauge theories, so one can at least try to sort of probe this using these formulations that we have expounded upon. So with this, I'll thank you for listening. And if there are any questions, please go on ahead.
Thank you, Shubham. Questions?
Hi. Thank you
Hi.
for a very nice talk. I had a question. Whether these duality symmetries have been extended to exceptional groups also, for example, in the case of n equals 8 supergravity in 4 dimensions, like this approach?
No, not yet. I mean, because this is fresh, but I mean, yes, in principle, it should be possible. Like if you have any twisted nonlinear self-duality, I see no reason why this construction cannot be generalized.
Yeah, because in n equals 8 also we have abelian field strength, not the non-abelian field strength. So it should be possible to extend this analysis there, right?
Yeah, absolutely, absolutely. It should be easily possible.
Okay, thank you.
Hi. In the slide where you introduce this harmonic, higher form harmonic symmetry, can you please go to the slide?
Yeah. You mean the abelian one or the non-abelian one?
I think probably in the abelian one, it's like in the beginning of it. Yeah. So here this this electric higher form symmetry that you have written del C equal to V to the 2n, which is some closed form. Is it like a large gauge symmetry, large gauge transformation kind of thing? Is that?
No, I don't think I will call it a large gauge transformation. I think I will simply call it just a higher form symmetry. I mean, it's essentially just simply saying that the Bianchi identity you can also think of as a conservation equation, and then you can say that what symmetry for which what is, using the Noether's prescription, that what symmetry for which is this a conservation equation, and that symmetry is this electric higher form symmetry.
Okay. I see. Thank you.
Any further questions?
Very interesting work, Shubhranil. Just one
thank
small
you.
question about the gravity couple part. You mentioned briefly. No, when you couple to gravity, you said that it will go in the interaction term. Is that only for weak gravity that you can deal in perturbation theory, or it is more generally you can do it for any gravity background?
No, so the original construction by the Sen and Lambert, it assumed that this star is with respect to eta, and then this gravity is something that we expand by eta. But this was generalized by Hull in 2022, where you can just do it by any background. So you can have this star with respect to any curved metric, and then this graviton fluctuations could be around that curved metric. So it doesn't have to be with respect to a flat background.
Okay. Thanks.
Yeah.
Any other questions? Okay, maybe I have one.
Sure.
So, because you have these higher form symmetries and etc., and also you're coupling with this extra field, do you have some new way of looking into the spontaneous symmetry breaking and Goldstone Morse, etc.?
Yes. I mean, there are like plethora of new things that can be asked in this point, because it's, for example, this is just simply telling you that there is a new paradigm of writing actions, right? I mean, because if you have this freedom of introducing extra fields which very cleverly decouples, then there are many more possibilities that opens up. So yeah, I mean, there are all sorts of things that can be asked. I mean, we are just starting out, so for sure, yeah, it's a valid question.
Okay, thanks.
Yeah.
Okay, so If there are no other questions, let's thank Shubhranin once again.
Yogesh, you want to come? Come here, come here. Shamik. Come. He's outside already. Okay, anyway, let's start the end of the conference. We are all very happy that all the participants and the speakers could make it to NISER and IIT Bhubaneswar. It was one of the first conferences, international conferences organized both by IIT and NISER. And as it is with organizing a conference with two different institutes, it's not an easy job managing two different, administrations, etc. But fortunately, we actually received tremendous support from both the institutes. Our department of physics, head of the department, and our director, they were all very supportive from the beginning. And same is the case. They will students, and without their help, it's just impossible. So most of us probably were holding the mic and trying to manage things. But you will all know that it's the background. It's I think if you guys can come up, Ajit and Devabrata and some of the students. Nishant is also here from NISER. Many students, Adrenil, play a big handout, shout out to all of them. So most of these people actually spent all the time arranging things. Yeah. We also have to actually thank our funding agencies who provided support. Actually, both the institutes also supported financially, and different guest houses, different flatlets, everybody actually contributed. We, of course, all the good things happen, we share, and one or two lapses which you faced, that also we all share together. But I think largely, we would like to say that I think this is the first conference and we tried our best. We hope to have all of you in future for much more productive meetings and schools and advanced conferences, which even NISER is trying to hold in future, and even we are planning from our side. So thank you all, and if I'll give the mic to you in case you want to say one words. I have said enough. So thank you all, and we wish all of you a safe journey back, and hope to see you, many of you, in future conferences. So Nishant is here. Thank you. Thanks a lot to all of you. Thank you.
Yalla.